So, good morning. Good morning and welcome everybody. So, after the very successful welcome reception yesterday, I want today now officially also open this conference. And with that, not only welcome you again here to the conference, but also welcome our first guest here. And it's a true pleasure for me to announce today Markus Blume, State Minister of Science and Arts of Bavaria. So it's really an honor, a pleasure for us to having him here at the Superconducting Qubits and Quantum Algorithms Conference. It shows prominently the value that the Bavarian government attaches to science and technology as the key elements, as really the basis of the competitiveness of the country and of the current and the future well-being. So needless to say, also without the long-term and sustainable support of the Bavarian, but also the German government, for example, realized by the Munich Quantum Valley, Munich, and also the many other funding schemes here, Bavaria would not be such a prominent place for quantum science and technology, home to this dynamic quantum community with all the commercial activities, science activities, and research activities. So with this, I thank you for coming, and please, the stage is yours.
So, good morning everyone here in this wonderful room. Welcome, as I can read here, to the leading conference on superconducting quantum qubits and algorithms. Thank you for organizing this conference, this event here in Munich, in Garching. Thank you to the organizers, to IQM, to Technical University of Munich, and all the other guys who made this wonderful event possible. It was a very wise decision to choose Munich and to come to Munich for this conference. Munich in summer has many things to offer, and in autumn, you know, we have this world-famous Oktoberfest. So unfortunately, your timing was not that good, because for the best part of the summer, you're a little bit too late, and for Oktoberfest, you're a little bit too early. But on the other hand, this means that your motivation is a very honest one. You're not here for the wonderful lakes, you're not here for the beer, you're here for the quantum stuff. And maybe the timing and this venue here is maybe the best choice you could make for this conference and to spend here a couple of days in Munich. So welcome to all of you to this conference. Indeed, as we just heard, Munich is, I believe, the place to be. Okay, I should believe this because I'm the responsible minister for science and the arts. But indeed, Munich has many things to offer. When it comes to the quantum world, I would say the Munich Quantum Valley is one of the leading initiatives, not only in Europe, but in the world. And in order to double-check, I just asked ChatGPT if it is fair enough to say that Silicon Valley and the Munich Quantum Valley is comparable. And ChatGPT stated, well, in essence, while Silicon Valley is a well-established global hub for broad technology innovations, Munich Quantum Valley is a new initiative primarily targeting the emerging field of quantum technologies. Both are crucial in their respective domains and contribute significantly to technological advancements on a global scale. Well, when our algorithms do believe that you can compare Silicon Valley and the Munich Quantum Valley, so they are basically in the same league, it's fair enough to say with all the natural intelligence that this is truly the case. We spent a lot to attract the best and brightest minds of the world, and we spend and invest a lot to strengthen our universities here in Bavaria. We just set up an initiative a couple of years ago called High-Tech Agenda Bavaria. It's a 5.5 billion investment program that brings 1,000 new chairs to our universities that is dedicated to bring new ideas in the field of super technology, in the field of quantum tech, artificial intelligence, new space to our universities in order to prepare the ground here for the talents of tomorrow. Quantum is maybe one of the most exciting fields. Not everyone does really understand what's going on there. And I just had the opportunity to look at one of the quantum computers at LRZ that was just set up there a couple of days ago. And it's not fair to say I would fully understand what's going on there, but I understand that it will make a difference in the future. It's a revolution of computing. And after reading the cheat sheet I just found down there, I understand a little bit better what's going on there when it comes to quantum computing. In any case, it's necessary to prepare the grounds, to move forward, to share new concepts, and in the end, to move forward in order to commercialize the opportunities of quantum computing. Here together, it's fair enough to say we have the brightest minds in this field here in this room, because it's the only conference in this field globally. And for this reason, we are really a little bit proud that you are here in Munich. We are very thankful that you spend your time here in Munich. And we wish you all the best for the upcoming days. Share your thoughts. Maybe choose Munich for making new investments here. Please be free to contact me afterwards, and I'm sure we can arrange a package designated for you. We wish you a good time, and maybe next time you come here to Munich with even a better timing, so maybe for the best part of the summer or for the Oktoberfest. All the best. Thank you.
Hey, good morning. Will Oliver with MIT, and it's my privilege to chair this first session of SQA 2023. I think we all are interested in seeing superconducting qubits be successful, and to do that, I think we all recognize that they need to be robust, reproducible, and extensible. And we'll hear a lot about that this morning in this session. After a nice kickoff from Shruti Pudi last night on quantum error correction, it's my privilege to introduce our keynote speaker this morning, Alex Bourassa, who will tell us about the latest work from Google Quantum AI. So please, let us welcome Alex Bourassa.
All right. Thank you very much, Will, for the nice introduction, and thank you for the organizing committee. This is a really wonderful venue, and we have an amazing list of speakers coming up, so I'm very excited. Speaking of, I was very inspired by the talk from Shruti yesterday. As you can imagine from the title of my slides, quantum error correction is very near and dear to my heart, so well, if I overlap in any ways, just consider it a repetition code. And if there's any discrepancy, just assume she was right. Okay, so my name is Alex. I'm a senior research scientist at Google Quantum AI. And today, on behalf of the whole team, I'd like to talk a little bit about suppressing quantum errors by scaling up the surface code. And so let's get started. I've divided this talk into 4 sections. First, I want to give you a little bit of an overview of Google's roadmap to build an error-corrected quantum computer. Then we'll talk a little bit about superconducting qubits, but since this is a superconducting qubit conference, I won't spend too much time there. I'm assuming a lot of you are very familiar with this, but it's always good to get a little bit of a review. And then we'll get into the meat of the topic, which is really about scaling up the surface code. And if we have some time at the end, we'll talk about some challenges and outlooks going forward. Okay, so let's talk about Google's roadmap for building an error-corrected quantum computer. This is, incidentally, is a view from one of the mountains, Santa Barbara. It's a beautiful place. If you're ever down there, just do come and find us, and we'd be happy to talk. So this is the roadmap that we laid out a few years ago for building an error-corrected quantum computer. It has several milestones that we're aiming to achieve, and some of them we've already achieved. The first one was doing a circuit that went beyond what was classically simulatable, and that milestone was achieved in 2019. And since then, we've actually updated those numbers with bigger and better hardware, and so we're doing something that's even more difficult for classical computers. But today what I want to focus on is the second milestone, which is really about building logical prototypes for a qubit. The idea here is really, the primary challenge here is really to talk about sort of building a logical memory. So we're going to be trying to encode a logical state into this surface code and then hold on for dear life for that piece of quantum information for as long as possible. This is sort of a critical building block for building computations, and so we think that it's a really important first step. All right, so we've been talking about error correction. So why do we need error correction? Well, I'm an experimentalist, so I work with physical qubits most of the time, and I like to think that we've made a lot of work in making those qubits a lot better over the years. We have error rates that are below, 1%, maybe on the order of 0.1%, and I can dream of a beautiful world where all of our gates would be at 0.01% of error. The problem is that when I go and talk to the people that do algorithms, they're like, well, it'd be really nice if we had something that was, 1 in a billion or 1 in a trillion error rates. And this is going to be just very hard to do with, single qubits. And so we really want to use quantum error correction here to bridge the gap between what's sort of physically realizable and what's, practical for that sort of algorithms. And this is where quantum error correction comes in. It really, promises to bridge the gap between those two things by trading many physical qubits that are okay with for one excellent logical qubit. And really here, this is sort of the tagline of quantum error correction is you put more qubits in it and it becomes better. But there's a disclaimer at the bottom here. This is what they tell you at the bottom of the advertisement, right? Which is, as long as the physical qubits are good enough. And this is a really important disclaimer because at the end of the day, if your qubits aren't good enough, what you're going to end up finding is that putting more qubits into your system is actually going to make things worse. Let's see here. Oh, yeah, there it is. OK. So yeah, ideally, you'd want to be in this regime here, where as you increase the size of your code, so each color line is sort of increasing the size of the code, the logical error would sort of go down. And this happens well once you're at a low physical error rate. Unfortunately, there's another regime up there where as you're making your code size bigger, your actual logical errors will go up. And this is the regime that I like to call more qubit, more problem. And we don't want to be there. So we want to be below the threshold, and this is what we're going to try to achieve today. OK. So let's talk about superconducting qubits very briefly. So the types of qubits that we like to use are these transpond qubits, which are a combination of a large capacitance with a Josephson junction. In fact, we use this loop of Josephson junction, and we do this because that allows us to tread flux in that loop. You can see here on this image, if I can point to it, this is the capacitance. This is sort of the Josephson junction, which are really tiny here. And you can shred some flux in this loop by using this flux bias line here. And that basically allows you to control the frequency of your qubit. So we have tunable qubits this way. OK, so the very first thing you might want to do with a qubit is do a Rabi oscillation. This is sort of the hello world of the quantum world. So you want to be able to control your qubit and flip it from the 0 state to the 1 state. The way that we do this is using this drive line on the side there that really allows you to sort of drive coherent, resonant microwave drive. For instance, it could be at the same frequency of your qubit, maybe something like 6 GHz, but it really depends on the design of your qubit. And so if you do this, you can see this sort of beautiful sine wave, which really tells you that you're flipping your spin from 0 to 1, and you can calibrate this such that you do exactly a pi, for example. Now you have single qubit rotations. Okay, what else would you like to have? Perhaps something like measurements. So once you're able to control your spin, you also want to be able to read it out. And the way that we do this is by coupling our qubit to a resonator. We do this using this capacitive coupling. And the way that the readout works is something called dispersive readout, which essentially just means that you don't tune your readout and your qubit to the same frequency. You tune them to different frequencies, such that they can't actually exchange information or energy. But what they do is that they push on each other. So in particular, if your qubit is in the 0 state, it will push the resonator down a slightly less amount than if it's in 1 state. So if in the 1 state, it pushes down the frequency of the resonator by a slightly larger amount. And that basically means that you've reduced the problem to try to measure the resonant frequency of that resonator. And you can do this by sending a probe tone to this top line there, and if you're on the left of that resonance, you'll acquire a certain phase shift, and if you're on the right, you'll acquire a different phase shift. And so that's how we do our readout. Now, another operation that's important to us is a reset operation. Fortunately, we can use actually the same resonator here to do this operation. What we do is we tune the qubit this time in resonance with that resonator, and now they can actually exchange energy. And so in particular, if your qubit started with 1 quantum of energy in it, if you tune it into resonance with the resonator, it will sort of swap it to the resonator, and the resonator will immediately proceed to lose it to the environment. It's sort of a leaky resonator, and so that's how we like it. And so this is particularly helpful for doing sort of reset within the circuits, to do it fast, and we can in particular use it for leakage removal, and we'll talk a little bit about leakage a little further down. Now we have all the single qubit gates that we want, control, microwave control, reset, readout. What else do we need? Well, we need 2 qubit gates. One 2 qubit gate that you can think about implementing is this I swap gates. And the way that this works is if you just capacitively couple 2 qubits together and you tune them to the same energy, they will start to swap photons from one qubit to the other. And in particular, this gate that it implements is an I swap, so they add an I phase onto it when they swap. We could go through the Hamiltonian and figure out exactly why that is, but believe me, there's an I there. And so that's how it is. Now, this interaction is very helpful, but in the case of the surface code, we'd actually like something more like CZ or C0 or something like that. It's more convenient for implementing the circuit that we need for the surface code. So how can we do this with this type of interaction? Well, we can use the same exact type of interaction, but now instead of tuning this 1001 energy level together, if we tune the 11 level with the 02 level, now we can start to do something a little tricky here, which is leave the computational basis. So you imagine that the computational basis involves only the zeros and the 1 state, but now we're going to go into this state that has 2s in it, and this is sort of a state you don't want to stay in. This is a leak state, right? But you can sort of transit through it, and in particular, you can do a full sort of swap to this 02 states and then back into the 11 state. And for each of those swaps, you're accumulating this I phase, remember? And so if you do it twice, you're going to get a minus sign that shows up. And as you can see, all the other states are sort of detuned from each other, and so they're not doing anything. So effectively, what you've done is you've implemented a gate where you get a conditional phase only when you're in this 1-1 state. And this is sort of the definition of a CZ, and so effectively that implements your CZ. So you can use the same exact interaction and implement a CZ. All right, so this was sort of the basic gates that we needed, but in practice, we actually want to calibrate each of those gates to a very high degree of precision, and to do this, we need a lot of automation. And automation is really critical for scaling. What I've shown here is sort of the graph of all the experiments that you need to run to calibrate just a single qubit pair. So this is all the single qubit experiment and 2 qubit experiments. Every bubble here corresponds to 1 experiment, so something like Rabi oscillation or a readout and so on. And so you can imagine that this is a lot of experiments to run, and doing this manually becomes very overwhelming very quickly. And if this is just for a single pair, you can imagine that having it for your whole processor becomes very crazy. Additionally, you can imagine how reliability is critical for these experiments. If you make your new calibration that's supposed to calibrate everything to a better degree than what existed before, but it only works 99% of the time. Well, you say 99% of the time is pretty good, right? But if you're running it on order 72 qubits here, and you're running it every day, I can guarantee you it's going to fail all the time, and you're going to spend all of your time trying to fix those failure cases. And so you really need to get your reliability for those experiments up as far as you can. And this is sort of a challenge, that I didn't used to think about when I was in grad school, but now it's something that's very relevant to our problems. Additionally, parallelization is important. Wherever you can do it, you should. For example, if you're running a Rabi oscillation on the corner qubit there, you can probably do it on some other qubits at the same time. And doing it that way really allows you to sort of get a constant scaling of the number of experiments you need to run when you start to scale the number of qubits. And so that's really important. Okay, another thing that you should think about, specifically for the types of qubits that we have, which are these tunable qubits with tunable couplers. We have all of these degrees of freedom, all of these knobs we can tweak to do our gates, which is great, but it also means that we have to select at which frequencies we're going to do all of these gates. And so at some point you have to sort of decide, and we have to decide in a way that maximizes performance. And the way that we do this is essentially by measuring a bunch of characterization data and then feeding them to an optimization routine that tries to extrapolate from physical model what kind of errors we expect for the different frequencies, and then optimizing over each of individual gate operating frequencies. And so this is another very important aspect of getting every ounce of performance that we can out of our processor. Okay. With this, let's get into the next section here, which is about scaling the surface code. The idea here is really going to be to compare a distance 3 surface code to a distance 5 surface code. In theory, a distance 3 surface code can handle any 1 error, and a distance 5 surface code can handle any 2 errors. And, however, the big challenge here is going to be related to that disclaimer I said at the beginning, which is that you really need to get those qubits good enough for it to matter at all. And in particular, what we're going to try to do here is to overcome the additional errors that's incurred from adding more qubit, and see if we can overcome that just by increasing the size of the code. So distance 5 code should have more error correcting capacity. So if we can overcome the additional error that comes into play because of that, that would be fantastic. Okay, so this is our latest and greatest processor. This is our 72-qubit Sycamore processor. We can embed onto this a distance 5 surface code. For these qubits here, the yellow qubits are our data qubits. So you see this 5x5 grid. And the blue qubits are measure qubits. These are the ones that we're going to use to do the parity checks. We have different shading here for the Z stabilizers and the X stabilizers, but essentially they're all doing similar stuff. And then we can implement sort of the logical operators, so the logical X and the logical Z as sort of the vertical line and horizontal line. So there you go. This is what our logical qubit looks like. Okay, so for those of you who are not familiar with the surface code, this is sort of a very, very brief sort of introduction to what you're trying to do here. Really, it's to take one logical qubit, distribute it across many physical qubit, distribute that state across many physical qubit. And then importantly, what you're going to spend all of your time doing is these parity checks. So you have X parity checks and Z parity checks, and so you're going to try to look at the parity of the 4 neighboring qubits or 2 neighboring qubits, depending on where you are. And this is sort of the bread and butter of this surface code. This is what you're going to spend all of your time doing, is these parity checks. So let's look at the circuit that you need to do one of these parity checks. It looks a little bit like this. If you look at it from the perspective of a measured qubit, the measured qubit's job is to do the parity check of all of its neighbors. And so the way that it does that, we can look at it. It starts, if you start into this 0 state here, we can do this because we can reset our state. You can then do a change of basis with this atomr, put yourself into the plus state, and then you're going to do between 0 and 4 flips of your state, and so you can think of these CZs as essentially conditional on the state of the data qubit, flip the phase of this measure qubit. And so you're going to do this between 0 and 4 times, such that you're going to encode the parity of that qubit on the phase of that measure qubit. Then you do a last Adamar to flip it back to the 0 and 1 basis, and then you can measure it and reset it. This is what it looks like from the perspective of the measure qubits. Now let's look at the perspective of the data qubit. The data qubit's job is to participate into the parity checks of all of its neighbors. And in particular, it has to do 2 parity checks in the X basis and 2 parity checks in the Z basis. And so let's start with the Z1. We do one of these CZs in that way, and then we're just going to use this Adamar to sort of flip the X and the Z basis, such that now the middle 2 are going to be checking the X basis, and we finish off with a Z basis here. And it's kind of nice to lay it out that way because you have symmetry, and symmetry is always nice. Okay, this is what it looks like when you put it all together. Looks kind of like this. You can calibrate or benchmark all of your component errors for every one of those components, and you can see that we have something on the order of 0.01% on the single qubit gates, and 0.7 or 8 on the CZs. Yeah, so this is great, but you can notice that here that the measurement and the dynamical decoupling here compose a significant portion of your budget, and the reason for this is because it is actually a very large part of your time is actually spent doing this measurement and reset. In fact, it constitutes about 70% of your actual cycle time. So in this drawing, they look like a squished up box, but in reality, it's a very long thing in time, and so that's why they incur more error. Okay, now let's look at sort of the day in the life of a logical qubit. Now remember, the goal of this experiment at a large scale is to encode this information and try to retain it for as long as possible. So the way that we do this is we start by running 1 round of the stabilizer measurement. This will project us into one of the eigenstate of the stabilizers. This is sort of our initial state, and we can call this the +1 state. And then we're going to do several rounds of the error correction. And for every round, we're going to compare the parity measurement from one round to the next, and we're going to call that a detection or detector. And so if those 2 parities don't match up, we know that some errors has occurred. And these errors can occur in different patterns, and depending on exactly where they occur in the circuit, they're gonna show up as different patterns of detection events. But ultimately, all of this is encoded in this decoder graph, which is going to be able to sort of tell you whether it thinks that the observable is still in the +1 state or if it has flipped. Hopefully, it's still in the +1 state, and if it is, we win. We've been able to get this memory experiment to work, and if it has flipped, then we call this a logical error. Okay, so now, whoops. Now let's look at some data. This is the data that comes out of our experiment, and in particular, what we're looking at here is the detection fraction probability. Now this is a really helpful metric to look at because it basically tells you how often errors are occurring. So this is not directly a measurement of logical error, but it really tells you how much physical errors are occurring in your system. So it's an important metric to look at. And if we look at this for the D5 and the D3 code, we can see that we have on the order for the D5 on the order of maybe 0.18 or 0.17 detection fraction probability. And for the D3 code, it's sort of similar. It's a little bit lower because, again, as you're adding more stuff into your system, you're making things harder. And so your errors are going to go up maybe slightly, but it's not going up dramatically, which is a very good sign that you might be able to gain something eventually when you add the effects of error correction in it. So this is very good. And in fact, we do this comparison with several D3 grids to try to be as fair as possible between a comparison for the D3 and D5. Okay, one of the things to notice here, it's a little hard to notice here, but there's a slight increase between the very first round and the last round. And this increase is on the order of about 12% over these 25 cycles. And we're attributing this to leakage. Leakage is a problem because it accumulates over different rounds, and so we're really interested in sort of mitigating this head-on. We don't want to do any type of post-selections. We think that this is going to be hard to scale eventually, and so we want to try to mitigate this leakage head-on, and we have techniques now to try to do this. We didn't use these directly in this paper, but we think that these techniques are going to be very applicable for the future. So basically, we use our reset gate to reset that leaked state. Okay, so once we have all these detection events, we feed them into our decoder, which has these, encoded in them the sort of physical error model. And the decoder's job is going to be to answer the question, is the corrected logical state still what it was in this initial state? And as I said, if it is, then we've successfully implemented our memory, and if it isn't, then we have gotten a logical error. So now it's interesting to look at this logical error over time. So as we increase the number of rounds, we're going to increase the number of logical errors because they have more time to occur. And so the question is, how fast are these logical errors accruing? And the answer is for D5 surface code, it's on the order of about 2.9%. And for D3, it's on the order of about 3.0%. And so, we have something that's slightly better for the D5 code, which is very encouraging. And so here, what we notice is that not only is it lower throughout this curve here, but actually the ratio. No. Okay, I think this is dead. Actually the ratio of from round to round is actually slightly lower, which is really what we care about. Is this lambda factor that we had before, which is the ratio of the error per rounds for D5 and D3 surface code. Okay, another way that's interesting to graph this data is to actually look at it from sort of a broader view and look at system performance over time. So this arrow of system performance is really sort of months of improving a hardware. And as we do this, we're of course going to increase the fidelity of our D3 code, and we're also going to increase the fidelity of our D5 code. But importantly here, our D5 code is going to increase faster than our D3 code because it's benefiting from this extra error correction. And so after we reach this point, where at some point we reach sort of this equality and we pass this equality, then we can sort of declare victory and say that we've successfully crossed the threshold where the D5 essentially beats the D3 grids. Now, the question is, are we there yet? Are we below threshold? The answer is, well, it's sort of complicated because there isn't a single threshold point. What we can say is that we have a D5 that beats a D3, but there's a whole set of other sort of crossing points up until, let's say, D25 beats, D17, and that crossover regime is really what we've entered. So we've been able to enter this crossover regime where now we expect successively, bigger codes to beat the smaller ones as we sort of improve the performance. But importantly, this crossover regime is pretty small. It's on the order of about 20% on the scale of the physical error rates. And so, that means that just by improving our system by a factor of 20%, we should be able to now leave that crossover regime. And we expect this to happen relatively soon. And at that point, we'll be well below threshold, and every bigger code is going to sort of beat the smaller code. And so, this is sort of a very important milestone for us and sort of demonstrating the power of error correction in that way. So at the end of the day, the larger code wins by about 4%, which is a small margin. But importantly, we've been able to demonstrate that we have sufficient system performance now to make up for the fact that we have a larger grid. So adding more qubits actually makes things better, which is really fantastic. Okay, and to conclude here, let's look at a quick outlook of where we're going with this. One of the interesting thing to look at is I've claimed at the beginning that error correction can make up for many orders of magnitudes in errors. Now this is sort of a you have to test these types of claims because it's not clear that when you get to these very low error regime, there's not going to be something else that come and sort of get you in trouble. And so, you know, one question one could ask is, can we really make up 5 orders of magnitude on scaling quantum error correction? And we think that the answer is yes. And the evidence that we'd have to this is that we can test this type of code using the repetition code, which is essentially a 1D simplification of the surface code. Only corrects for 1 quadratures of error, so it's not a full quantum codes. But it's very similar in many ways. But it has 2 characteristics that are kind of nice for these types of tests. It has a higher threshold for errors. And it also, you can scale it by using less qubits. So we can implement a full D25 grid on the same sort of footprint as we do our D5 surface code. And because the threshold is higher, we can actually start to benefit from the exponential scaling. And we can actually explore these low logical error regime using that code. And that actually sort of allows us to see what kind of error could start occurring. Now, the first time that we did this, our curve started to flatten out a little bit at an error in a million, which is pretty low, but you know, that's a little concerning. We want to go below that. And it turns out that what was happening there is that we were seeing these high energy impacts. So whenever this high energy impact sort of happened on our processor, it just messes up all the qubits everywhere on our surface code. This is a problem because the surface code is not very good at compensating for all of these correlated errors happening at the same time on the processor. And so it's really important that we think about this problem. This is something that, you know, we're going to be thinking about in the future. And when we start to reach these low error regime, it's going to be something that we need to think about, you know, solving essentially. So for future experiments, you know, we are currently only at the lambda of 1.04. This may not sound impressive, but this is where your exponential scaling really starts to kick in. Now, every improvement that you make to your processor is going to sort of exponentially improve your logical memory. And so, in this work, we have this sort of flat line. It's slightly going down by 4%. But it's essentially flat. But in future work, we hope that we get to these lambdas of 2s, 3s, and 4s. And at that point, you're really getting that exponential sort of improvement really kicking in, and the improvements are going to go really fast at that point. So we're really excited for this. We have an error budget of where we think all of our error sources are coming from. We have this pretty well characterized, and we're sort of confident that we can reduce some of these errors over time. So with this, let's point towards the future. This is the next milestone we want to achieve. This is our milestone 3, which is going to be attempting to make a long-lived logical qubit. Now we're going to have to improve our processor into 2 dimensions here. We're going to have to make it every single qubit's more performant to increase that lambda value and really get that exponential scaling. And we're going to also have to increase the number of qubits to really benefit from these higher distance codes. And so there's going to be these 2 dimensions of improvements. If we could do this, we hope that we can then demonstrate a really long-lived logical qubit. So we're going to have something that lasts for many, many cycles. Okay. So with this, I hope that I've motivated why quantum error correction is important for us. We've demonstrated that we have a D5 grid that modestly outperforms our D3 grids. And hopefully, I've gotten the message across now that if we can improve slightly our logical error rates and we can make our grid bigger, we're going to get something that really kicks in as an error correction mechanism. So with this, I'll conclude. If you guys are interested in our team, there's a URL here, or you can come and chat with me anytime during this conference, and I'll be happy to chat. So with this, I'll take any questions.
Okay, great. Thanks, Alex, for a fantastic talk. We have time for a couple questions, and I know we've got some here, so we'll start with Mikko.
Great, Alex. Thanks for the nice talk. It's great work that you're doing. I just wanted to ask you, maybe you could a little bit more elaborate on the system improvements. Like, okay, some improvements may be a little bit trivial, but what are kind of the non-trivial improvements or some improvements that could perhaps come, more challenging when you increase the number of qubits? Like now you assume kind of that the lambda is staying constant, okay? On the repetition code side, you kind of showed that, that works, but maybe there is something in the surface code which is more challenging that would kind of challenge that assumption. So could you elaborate a little bit on that?
Yeah, for sure. So there was a couple points there. One was related to performance of our qubits, and I can look backwards and forward in time for the kinds of improvements that we're talking about. One of them was sort of what we had to do for milestone 2. These are things like improving calibrations of our gates, improving decoder, that kind of stuff. Looking forward, there's all sorts of improvements we need to have. In particular, we probably want to do things like improve T1 dephasing, crosstalks. Those are our main sources of errors as we lay down on this error budget. And I think we have good ways, good reason to think that this is going to happen. And then on the question of sorry, can you remind me what is the second part there?
Like the lambda dependence on D. Like that.
Yeah, that's right. Oh, yeah. So, okay, so there was this question of whether sort of you could extrapolate what was happening with the repetition code to the surface code. The answer is that's our only tool really at the moment, right? We can't measure on the surface code, and so there may very well be something that shows up on the surface code that wouldn't show up on the repetition code, but it is a good test. It is a very similar circuit in the way that it's implemented. It has a very similar sort of ratio of measurement and gates, and it's very similar in many ways. So we hope that it's representative, but of course I can't prove that to you, and hopefully, as we scale up the surface code, we can see if something else is a blocker, but I'm hoping that that's not the case, yeah.
Hi, I had a very short question. So I was just curious why dynamical decoupling forms such a large part of your error budget. It should just be pi pulses, right? So.
Yeah, that's right. So the reason is because it's composed of a large part of our time cycle. So essentially, our measurements and our readout, like I said before, is about 70% of our cycle. And so that's sort of the longest part of our operation. So things like T1 and T2 come in and really hurt you at that long scale. And this is why dynamical decoupling is causing problems. It's not because of the pi pulse, it's just because of the length you have to keep your qubit alive, yeah. Yeah.
So in the interest of time, I think we're going to have to cap it at 2 questions, but let's thank Alex again. Thank you very much for a fantastic talk. And so now we'll kick off the first session. We heard from Shruti last night about the importance of erasure errors, and we will now hear about an experimental demonstration of a dual rail encoding in cavity qubits. And for that, please welcome Patrick Winkel from Yale University.
Hello, everyone. My name is Patrick. I'm a postdoc with Rob Sholkoff at Yale University, and today I want to talk about a new encoding that we developed that makes use of supergalactic cavities and utilizes their intrinsic noise bias and also uses the concept of erasure conversion for quantum error correction. And besides my colleague and friend James Teo and myself, you can see that a lot of people actually contributed to this work, both from Yale University and also from quantum circuits. So when I say quantum error correction, what I mean or what I think of and what we just heard about is the surface code. And it's a lucky coincidence that we just heard this wonderful talk by Alex, so I basically can go over this slide very briefly, but maybe I want to summarize the main important aspects here. So in order to protect our quantum information from physical errors in the hardware, we encode it redundantly in a 2-dimensional grid of physical qubits, which we see here on the left-hand side. And the premise of the surface code is that if the physical error rates that happen in our hardware are below a threshold, by increasing the distance of the code, we can actually suppress the logical error rate. And the threshold is usually found numerically, and on the right-hand side, we see an example of such a simulation where we have on the y-axis the logical error probability, and by scaling the physical error rate, we see that, yes, there is this crossover point which is on the order of 1%. It depends on the error model that we're using. And then below this threshold, we see by increasing the distance, we do exponentially suppress the logical error rate. But this only happens very efficiently if we are well below this threshold. And as we've seen, this is very hard to achieve with superconducting quantum hardware. And the scaling that we find for Pauli errors is the distance plus 1/2. And naively, we can understand this scaling by how the surface code corrects for Pauli errors. And we never directly detect where an error has happened, but from our syndrome measurements, we can only infer what is the most likely error event that has caused this error syndrome. So the surface code or the decoder only infers the error. And as we have learned yesterday by Shruti, there's this other class of errors that we call the erasure errors. And an erasure error is an unknown error that has happened, but we actually know the location. And this additional information is actually quite beneficial when we look at the scaling of the logical error rate. So first of all, we find a threshold which is around a factor of 4 to 5 higher than the one that we find for Pauli errors. And we also see an improved scaling because our surface code is more resilient against these erasure errors because we know where it happened. And this has been looked into by Shruti and Jeff Thompson in this publication, but the concept of erasure errors is well known for decades already, and we do find that the threshold is indeed higher, and we also do find an improved scaling, which is not clearly visible here on this log-log scale, but you can read the paper, and it's definitely scaling with the distance d. And what is very important that we can convert most of the Pauli errors into erasure errors. So we need to have this measurement in order to convert the errors. And so this is a very interesting concept. And so the question would be, how can we translate this concept to the superconducting quantum circuits community? And we looked into linear cavities, 3D cavities. And what we want to make use of is the intrinsic noise bias of these cavities. And this is a very standard experiment for us. So this is a 3D stop cavity, but it could also be a different type of linear oscillator. Here, the resonance frequency of this mode is defined by the length of the stop, which forms this quarter wave resonance. And because this is a linear system, we need nonlinearity to prepare and read out non-classical states in our system. And for that, we insert a trans-1 ancilla, which is just a single chosen junction shunted by a large capacitor, and the two modes interact capacitively. And when we look into the physical error rates in these systems, we find this error hierarchy. So the dephasing time in these cavities, the intrinsic dephasing time, is very long, and this has been demonstrated in multiple experiments, and we will actually later today hear a very interesting talk by the group of Serge Rosenblum from the Weizmann Institute. And the dephasing time is significantly longer than the energy relaxation time. And what we actually find is that the most likely errors that can happen in our system is due to the trans-1 ancilla. But overall, we find this error hierarchy, which is very appealing for the idea of erasure conversion, because our strategy will be to find a way to convert the most dominant errors that happen in our system into erasure errors. And ideally, we're left with a low floor of Pauli errors caused by pure dephasing. And so let's start, how do we convert those errors into erasures? And transforming or detecting photon loss has been around in the linear quantum optics community for a very long time. And the answer to this question is the dual rail encoding. And I also would like to emphasize that similar ideas have been explored already in the superconducting quantum circuits community, also in the groups of Will Oliver, and more recently at AWS. And the idea is that we store our information not in a single cavity, but we store it in two cavities. Those will form our two rails, And our logical code words will be a single photon in one of the cavities or a single photon in the other cavity. And the measurement syndrome that we can use in order to detect single photon loss or single photon gain will be to measure the joint photon number parity. And we can see this by looking at the low energy spectrum of the system. A logical subspace is spanned by the single photon eigenstates of the system, and then all other states which form the leakage states have even joint photon number parity. And in order to complete the architecture, because we need to control it, we need to read it out, we also, in addition, need a transmon ancilla, which is capacitively coupled to at least one of the cavities. And we will use this extensively for state preparation, readout, erasure detection of photon loss in the cavities and our 2-qubit gates. And in order to implement single-qubit gates, we need a switchable beam splitter interaction. And here I would like to emphasize that the cavities are not at the same frequency, so a bit flip caused by a swap of an excitation would be very unlikely. And we also operate the transmon in the GF manifold such that we have this additional leakage space also for the transmon spanned by the E and the H state, which we can use to detect relaxation of the transmon. And yeah, the interaction that we're using between the cavities and the transmon will be the well-known dispersive interaction. Okay, so how do we actually control this system? So the nice feature, as I already pointed out, is that single qubit gates are actually pretty simple because they can be activated by this beam splitter interaction. So on the right-hand side, we see the logical Bloch sphere, which is spanned by the single photon subspace. And we can control the polar angle by the beam splitter rate and the duration of the gate. And we can control the phase by the beam splitter phase. And such an interaction, such a switchable beam splitter interaction, has been demonstrated in our group with 2 different types of couplers. And today I would like to emphasize the work of my colleagues Yao and Aniket that have used a flux-driven DC squid coupler in order to implement this interaction, and they performed randomized benchmarking on it. And for the raw data, they already find a fidelity of 99.92% for these beam splitter-like gates. And the duration of the gate is around 100 nanoseconds. And by performing post-selection on single photon loss, they can actually boost this fidelity to 99.98%. And if you would like to learn more about this experiment, I can highly recommend the poster by Aniket today, so please check it out. The next thing on the agenda is the logical readout. So how do we actually perform this end-of-the-line erasure conversion or detection of photon loss in the cavities? We can look into the logical readout. So for a single transmon, when we perform a projective measurement, we find this measurement histogram here that we see on the left-hand side, and we can clearly see the 2 pointer states which are associated to the transmon being in the ground and being in the excited state. So when we try to assign a state to the transmon, we go from the physical state that we see on the left-hand side to an assigned state on the right-hand side. And most of the time, we get this right. But there is a small probability of misassignment due to photon loss during the readout or due to the finite overlap of these pointer states. And the overlap the error due to this overlap is pretty small, so the fidelity of measuring the ground state is pretty high. But any single error in this measurement will give rise to a misassignment. And this is a bit different in the dual rail because now we combine 2 measurement outcomes. So there will be an operation that we use to map the state of the cavities onto the transmon. This can be a selective pi pulse, it can be a parity measurement. This is up to choice. And then we will read out the transmon. And so it doesn't need to be 2 distinct transmon. It can be the same transmon because we can use the high fidelity swap operation to swap states around between the cavities. But then we can use this combined information, and in order to confuse a state within the logical subspace, we actually need 2 readout errors. And most single errors in this readout will give rise to additional erasure, but this is not a problem because the threshold for the erasures is higher. And so we can use this high fidelity readout in order to perform, for instance, a bit flip experiment on on a system like that. And the two important metrics that we look at is the bit flip fraction and the erasure fraction. And this is a measurement taken from this publication from QCI that has been recently published or uploaded to the archive. And so what we see is that when we prepare the system in the logical zero state, we can measure the bit flip fraction, which means it's the number of measurements with respect to the total number of measurements that we performed, where we actually find the system in the other logical state. And we see that the increase is very, very tiny. And due to the high fidelity of the readout, we can see that the state preparation and the spam errors in this combined measurement is actually pretty low. And the other metric, what we can see is the erasure fraction. So this will be the number of measurement outcomes where we find the system outside of the dual array subspace. And this is dominated by decay into the common ground state. And from our model, we can actually see that this increase in the bit flip fraction is actually due to a misassignment of this common ground state into one of the states of our dual array subspace. And we can perform the same measurement for the other logical state, and we see a slightly different increase in the erasure fraction because this cavity has a different T1 time. But from the short time data, we find an apparent bit flip time on the order of 80 milliseconds, which is again dominated by the fact that we confuse states that are actually in the common ground state with one of the logical states. So this demonstrates so far a classical bit. So we need to look into the phase coherence, and we can look into the phase coherence in the same way that we do it for a standard two-level system. So we can perform a Ramsey type sequence. We prepare a single Fock state in one of the cavities. We use our calibrated beam splitter interaction to prepare a superposition state. We increase the idling time, followed by a second pi over 2 pulse, and then we perform our logical readout in combination with this end-of-the-line erasure detection, which means that we post-select, in this case, on single photon loss in the cavities. And what we find is that because we have a finite detuning in our operation, we see these characteristic Ramsey fringes, and from the envelope of these Ramsey fringes, we can extract a dephasing time on the order of 2.5 milliseconds. All right, this is already quite promising. It's not yet there where we want it, so we are currently working on trying to improve this number. But it's a good starting point. But what we see is that, again, when we look at this erasure fraction, the erasure fraction, so the number of measurements that we will throw away, is actually increasing exponentially over time. And we cannot use our end-of-the-line erasure detection for this because this measurement is also projective in the logical subspace. I mean, it's our readout, so it's more or less a byproduct of our readout. So what we need is a measurement that can detect photon loss in the cavities throughout the sequence without projecting the states in the logical subspace. And if you remember, zero? Okay. Yeah, if you remember, the states in the logical subspace have an odd joint photon number parity, while all the surrounding states have an even joint photon number parity. So what we need to do is we need to have a measurement of the joint photon number. And there is already a measurement of the parity in a single cavity, and this has been around for almost 10 years now. And we can use, on the left-hand side, you see the hardware. It's a single cavity coupled to a transmon. And we use this dispersive interaction and perform a Ramsey type of sequence where we prepare the transmon in a superposition state. And if the gate duration is matched with the dispersive interaction, what we find is that we map the even Fock states onto the F state at the end of the sequence, while we map the odd Fock states on the ground state, while we reserve the E state as a flag state for transmon decay during the sequence. And so in order to measure the joint photon number parity, we have the second cavity, and we can use at the same time, while we're letting this dispersive interaction act, we activate the beam splitter interaction, and we use a finite detuning. And if we get the parameters right, and more details can be found in this publication, or in these two publications here, then we can map the even states, or the even joint parity states, to the F state, and the odd parity states to the G state of the transmon. So E, again, flags transmon decay during the sequence, while F will indicate whether or not a photon has left our dual rail subspace. And so we can actually use this very same construction also to implement our 2-qubit gates. And the interesting part, or the very beneficial part for us, is that even though every qubit is composed of 2 cavities, we actually only need nearest neighbor interaction with, again, this beam splitter type of interaction. And the gate construction, the 2-qubit gate that we are choosing, is the C0 theta gate, which is locally equivalent to a C0 gate, or a conditional C gate if the angle is pi/2. And we can use this very same joint parity construction to perform our 2-qubit gate. And at the end of the sequence, if we measure the state of the transmon, the ground state will indicate success, while the E and the F state will indicate that something went wrong and we need to erase the qubits. And the duration of this gate is going to be on the order of 1 to 2 microseconds, and this needs to be compared, if we detect all first-order errors, to the intrinsic dephasing time of the cavities. All right, and because this nearest neighbor interaction is enough for the implementation of this 2-qubit gate, what we can envision is sort of a surface code composed of these dual rail qubits, where the dual rails both form the data qubits and the measurement qubits. We can think about how we assign the ancilla transmons. We can actually only put them to the measurement qubits, such that we presumably reduce the dephasing in the cavities even further. And this will, what we pay for that is a slight overhead in the components that we need for this. And with this, I would like to conclude. So I hope that I convinced you that this new paradigm is very interesting, that the dual rail concept introduces erasure conversion and error detection to quantum error correction, and that the system that we want to use has the ideal error hierarchy. I demonstrated a universal gate set, which is error detectable, including first-order errors of transmon, which is very important because this is going to be the most important, or the most dominant errors in our system. The single qubit gates are very simple, fast, and have a high fidelity. And ideally, the performance of our system should increase quadratically with improvements in the transmon coherence, because we're insensitive to first-order errors. And the outlook will be that we need to understand the limits on the phase coherence, and we want to demonstrate the 2-qubit gate and the erasure check. And with that, I would like to thank you for your attention.
Yeah, thanks very much, Patrick. Fantastic talk and work. I'm afraid that we're a little bit behind schedule, so I'd like to encourage questions during the coffee break. So thank you very much for the talk. Let's thank Patrick again. And let me also welcome the next speaker to the stage, Luca Hofele from ETH Zurich. And he'll speak about fast flux activated leakage reduction unit. So please take it away, Luca.
Can you hear me? Good. Thanks a lot for the introduction. I'm very happy to be here today and be able to present some of the work that we have been doing with our group at ETH in Zurich. Now, if you happen to have been here already last year at the conference, you might be familiar with this picture that I show on the title slide here, because it also has been the picture of a title slide of a talk last year, namely by my professor Andreas Varov, who has been presenting our latest results on repeated quantum error correction using the surface code. Now, back then in the experiment, the dominant error source that we encountered was leakage, and you already have heard yesterday that leakage is the most detrimental error source for error correction. And today I'm going to explain to you how we tackle this problem by implementing a fast, flux-activated leakage reduction unit. Before I start to go to the details, I want to quickly recap what also has been already mentioned by Alex, namely why we actually need quantum error correction. Now, as Alex has already pointed out, quantum error correction is going to be essential for maintaining quantum coherence and being able to execute large-scale quantum algorithms using a universal fault-tolerant quantum computer. Alex also has already showed you the surface code, so I'm also going rather quickly over this. There has been some very remarkable experimental demonstrations of quantum error correction using the surface code, but all of these first demonstrations suffered from leakage, which is, as I already pointed out, a detrimental error for error correction. So I quickly want to explain now what leakage is and how we can deal with it. As this is a superconducting circuit conference, you probably all know that our qubits are actually not real qubits, but they are just defined as the two lowest energy eigenstates of a higher dimensional system. And we sometimes make use of these higher energy states to implement 2-qubit gates, for example, the CC gate. But imperfect implementations of these 2-qubit gates can lead to finite population of these higher excitations, and this is what we call leakage. Now, to mitigate leakage, there's basically two main possibilities. One is a reset operation where we bring back the qubit, and by qubit I mean now here this higher dimensional system, but for simplicity I'm going to call it qubit. We bring back the qubit into its ground state. This is applicable to auxiliary qubits, which are used to measure the stabilizers of error correcting code. But it's not applicable to data qubits because we destroy the information encoded in a computational subspace. To this end, the idea of leakage reduction units was developed. Leakage reduction units work in the way that they remove leakage from higher excitations and bring it back into the computational subspace, but they leave the computational subspace unaffected, meaning they act as an identity gate on the computational subspace. Therefore, leakage reduction units are applicable to data and auxiliary qubits to mitigate leakage. Now, there has already been done quite some work both on reset and leakage reduction units, and I want to put our work quickly into context here. Starting with reset, there are three main approaches that I want to discuss here, and they all have in common that the idea is to swap population from the qubit into a dissipative element, which then quickly decays and brings the qubit back into the ground state. Now, the first approach is based on a microwave drive and was actually also implemented by our group at ETH, by Paul Manier and colleagues. Then there's Google's adiabatic swap that Alex has quickly mentioned, and a parametric flux modulation-based reset by Sue and colleagues was also implemented. Moving forward, leakage reduction units were developed by Markus and colleagues in Delft, and Google has extended its reset scheme to a leakage reduction unit by applying two resets interleaved by a leakage swap. Now, our leakage reduction unit is based on a parametric flux modulation, and it's going to be the topic of this talk. To explain the main idea of our leakage reduction unit, we first need a flux-tunable transmon qubit. And like for the other approaches that I have shown before, we need a dissipative element that we can swap our qubit population into. We use the readout circuitry for this purpose, which is already coupled to the qubit, and it's strongly dissipative because it's strongly coupled to the readout line. We then need a parametric flux modulation of the qubit via its flux line, and this modulation is going to be a cosine pulse of modulation frequency omega m and flux amplitude phi a. And it's going to be translated in a modulation of the qubit frequency with modulation amplitude omega a and modulation frequency omega a, modulation amplitude, sorry, omega a, and modulation frequency 2 omega m. This therefore creates frequency sidebands of the qubit, shown here by the blue dashed lines. And if we choose omega m such that the sideband of the F0 level is resonant with the E1 level, we can swap population from F0 to E1. Now, since the readout circuitry is strongly dissipative, this E1 state will quickly decay into E0 and brings us back into the computational subspace. Note that this coupling G, by which we couple from F0 to E1, depends on the modulation amplitude omega A, which we will come back on the next slide to. Having understood the main idea of our leakage reduction unit, I want to explain to you how we can calibrate and characterize it. To remind you, we need 3 main parameters to tune our leakage reduction unit. First of all, the modulation amplitude. Secondly, the modulation frequency. And finally, the duration of the pulse. To calibrate the leakage reduction unit, we first prepare the F state, since this is the state that we want to depopulate our qubit from. And we then sweep the modulation amplitude and the modulation frequency for a fixed duration of the pulse of 100 nanosecond. This gives us such a 2D landscape as shown here, where we can see that there are several resonances that allow us to depopulate the qubit. The 2 strong stripes on the right side are the F0 E1 transitions that I have explained on the previous slide. And then there's some further resonances which are second harmonics of the F0 G2 transition, which I'm not going to talk about in detail here. We then choose a particular modulation amplitude, and we choose a modulation amplitude of about 100 to 150 megahertz in order to keep large detuning between neighboring qubits in the surface code and reduce errors. We then find the corresponding modulation frequency in order to hit one of those resonances shown by the purple dot here. Having fixed those 2 parameters, we finally sweep the duration of the modulation, and we see that the F level shown here by the red dots undergoes these underdamped oscillations, and we can make use of the first minima of the F level to define the leakage reduction unit operation time, which we can see can be reached within 35 nanoseconds, which is on the order of our single qubit gates. We also see that our experimental data is in good agreement with numerical simulations based on master equations, shown by the solid lines. Now that we have seen that we can strongly depopulate the qubit, we also repeat this process for different modulation amplitudes and find that as we increase the modulation amplitude, we can even further reduce the duration of the leakage reduction unit. Now, having verified that we can strongly depopulate the F level, we need to check the second requirement for a leakage reduction unit, namely that it acts as an identity gate on the computational subspace to leave the encoded information untouched. We therefore perform interleaved randomized benchmarking, where we perform a sequence of n Clifford gates followed by a recovery gate, and we measure the G-state population of the qubit. We perform the same experiment, but we interleave the leakage reduction unit between each Clifford gate. And from the 2 exponential decays, we then find the error of the leakage reduction unit to be 0.25%, which again is similar to what we can achieve with our single qubit gates. The idling error of the qubit just during the leakage reduction unit is 0.1%, so we also don't increase the error significantly above what is achievable by decoherence. Now, having verified the performance of the leakage reduction unit on the computational subspace, as well as having seen that we can strongly depopulate the qubit, we want to put the leakage reduction unit into its main application, which is a repeated stabilizer measurement. For this, we apply the leakage reduction unit on an auxiliary qubit of a weight 2 stabilizer. In this circuit here, this is basically shown this repeated stabilizer measurement where we apply the leakage reduction unit just before the readout. Then we have a couple of single and 2 qubit gates just before the readout to map the parity of the data qubits onto the auxiliary qubits. And we have a final readout of all 3 qubits after the repeated error correction. To begin with, we compare the leakage accumulation with and without the leakage reduction unit, here shown by the open and filled dots. And we can find that the steady-state leakage population is strongly reduced by a factor of 10. Most importantly for stabilizer measurements are the mean syndrome elements, or what Alex has called the detection event fraction. And basically, as he has already explained, a mean syndrome element of 1 means that many errors get detected, while 0 means no errors are detected, which is the ideal case. So you want this number to be small, but you also want it to be constant over the number of cycles to be able to repeat error correction. If we don't apply the leakage reduction unit, shown here by the open circles, we can see a strong increase in the mean syndrome elements, which is a big problem for error correction. And therefore, what has been done so far and in the experiment that Andreas presented last year is to post-select on no leakage events, which is shown by the dashed line here. And by doing post-selection, we can see that we can strongly reduce the mean syndrome elements, but this has the problem that we have to discard a lot of, or a certain fraction of data each round, which is hard to scale. When we apply the leakage reduction unit, we can see that we can strongly reduce the mean syndrome elements as well, with the big advantage of not having to discard any data in any round. With this, I want to wrap up. We have demonstrated a fast flux-activated leakage reduction unit, which is as fast as our single qubit gates and has very low error on the computational subspace with 0.25%. We used the leakage reduction unit in a weight 2 stabilizer and showed strong decrease of the leakage accumulation by an order of magnitude. And most importantly, we were able to reduce the mean syndrome elements and reach the performance almost as good as when doing post-selection. As a next step, we want to investigate the use of the leakage reduction unit on data qubits and finally implement it in a surface code experiment. With this, I'm done, and I'm happy to take your questions.
Okay, we have time for 1 or maybe 2 questions. Oh, I see one here. Yeah.
Hi, Luca. Beautiful talk and really beautiful data, of course. So you showed this benchmarking experiment where you showed that the LRU had this 0.25 error. But do you know what the error actually is? I mean, so that's a number, but what really happened in the computational subspace? Phase errors, or do you know what happened?
Yeah, so we think that in addition to the decoherence that we anyhow see at sweet spot already, that we have to cross some small 2-level systems several times when we apply the modulation. And in addition, we also get some additional dephasing because we are away from the first order flux insensitive position. So I think it's a mixture of both dephasing and energy relaxation. Yeah.
Cool, very cool.
Thanks.
Okay, one more quick question. Oh, right there, yeah.
Hi, thanks for the very nice talk. And because your research is based on the loss of photons in your resonator, What I'm afraid is that does it work for superposition state of ground state and excited state, because it's not a unitary operator. But I'm sure it will work for ground state, pure ground state, or excited state. Can you comment that whether it will work for the superposition state?
I'm not sure if I understood you correctly, but you're talking about the qubit being in a superposition state and the resonator defacing the qubit because of photons in the resonator?
No, because if it's in a superposition state, your resonator loses a photon, E1 goes to E0, then you get a mixed state, right? You are not in a superposition state anymore.
Okay, so you're saying that when we're in the E0 plus the F0 plus the E1 superposition state? Sorry, I'm not sure I understand the question.
Okay, maybe let me ask in a different way, because I see this process as a non-unitary operator. So if it's a non-unitary operator, I would naively expect that the result, if you apply to a pure state, it will end up in a mixed state. Am I wrong, or did I miss anything?
No, so I agree. I would say you still end up in the pure state of E0, but when you start in F0. But the problem that you might encounter is that if your resonator is not completely in the ground state, then you would never go completely from F0 to E1, because you always already had something in your resonator, and this would create a superposition state, which then, if the resonator decays, brings you in a mixed state. But since the resonator is strongly depopulated, and as we can see by our experiments, below 1 per mil population, this should not be an issue. Maybe I still didn't get your question, but then we could also discuss afterwards.
Okay, I think we'll have to cut it there. Let's thank Luca again. And now I'd like to welcome to the stage Professor Benjamin Huard from ENS Lyon, who will talk about passive 2-photon dissipation for bit flip error correction of a CAT code.
Your signal 5 after 10 minutes, then he shows 5 after 15, he shows 0 for questions. This is better.
Yeah, this is great. Yeah, okay, thanks. Yeah, thanks a lot for the organizers to letting me present our work. So this is a joint work with the startup company Alice and Bob and my group at ENS de Lyon. And so I'm going to tell you about our experiment on the autoparametric CAT, which is a way to extend the bit flip times of CAT code up to 0.3 seconds and hopefully more later. So we already had a great introduction on the surface code. So there are various quantum error correction strategies. So we saw the surface codes in previous talks with beautiful experiments. There are other kinds of codes, such as the one that Patrick presented, where we actually encode a logical qubit in a high-dimensional Hilbert space, that of a cavity, for instance. And the game here is to identify a 2-dimensional logic subspace, so the code space, inside of this large Hilbert space, and use the other dimensions to correct for errors. And in our case, we like CAT codes. So the CAT code is and specifically during this talk, I will talk about the 2-leg CAT code. It's a scheme in which okay, so there's no pointer, but it's okay. So the 1 and the logical 0s and 1s are represented as coherent states, alpha and minus alpha. And so that the superpositions of those are CAT states, for instance. And the big advantage of this code is that if there are local errors, such as the main errors like loss of a photon or dephasing, then you see that as the size of the CAT code increases, so as the number of photons alpha square increases, there is exponentially less probability to have X errors, so bit flip errors, and only linearly more phase flip errors or Z errors. And so this is true only if we are able to stabilize the code space. So we need to stabilize, essentially, make it so that this cavity stays in the subspace span by alpha and minus alpha. And to do that, we can either use measurement-based feedback, reservoir Hamiltonian engineering, such as the Kerr codes, the Kerr cats, or dissipation engineering, which is what I'm going to discuss now. And so to tell you how this can be engineered, so the idea is that we have a memory cavity which will encode the logical qubit. And this memory cavity will be coupled to the environment through a nonlinear coupler, which, so precisely the subject of this talk is to present a new nonlinear coupler. And it's done in such a way that if we drive the coupler, then this drive will create a 2-photon drive input on the cavity instead of the standard single-photon drive input. And likewise, there will be a 2-photon dissipation coming from the cavity into the environment at a rate kappa 2. So if we combine these two drive and loss mechanisms, we end up with an effective loss operator, sorry, which is in a squared minus alpha squared. And this loss operator stabilizes the coherent states alpha and minus alpha, and so the whole code space. So this is how we do it, but when in practice, there are always parasitic single-photon losses at a rate kappa 1. And it's essential for this cat code to be useful to reach a very, very large ratio between the 2-photon loss mechanism, so 2-photon loss rate kappa 2, and the single photon loss kappa 1. And so to get this ratio high would improve the scaling factor, so how fast the bit flip time rises as a function of number of photons. It will also improve lower the duration of gates, and so it will reduce the number of errors during the gates. And finally, there is some kind of threshold above which this ratio permits to create a repetition code of out of these cat codes. And so there are various ways to realize this nonlinear coupling. So the way that's been used in the past is to couple the memory mode to another buffer mode which is wide open to the environment. And the two are coupled with a 4-wave mixing element. And doing so, it's possible to pump this 4-wave mixing element at the difference frequency between the memory, between the buffer mode and twice the memory mode, in such a way that we convert 2 photons from the memory for 1 photon of the pump and 1 photon of the buffer, which in the end realizes a 2-photon exchange mechanism between 2 photons of the memory for 1 photon of the buffer. And ultimately, because the buffer is open to its environment, if we adiabatically eliminate the buffer, it induces a 2-photon effective loss mechanism for the memory. So this worked great, and there are several papers that realize this 4-wave mixing element with first a transmon and later with an asymmetrically shunted squid. And so what I'd like to tell you here is that we have found a new way to increase the kappa 2, so this 2-photon loss rate, by going from a 4-wave mixing element to a 3-wave mixing element. So essentially, by removing this pump term in the Hamiltonian, we are able to enhance sizably, considerably the coupling between these 2 photons in the memory and the single photons in the buffer. And so the only trade-off is that we now need to ensure that there is a frequency matching condition between twice the memory frequency and the buffer frequency. But if we manage to do that, then indeed we should have a much larger 2-photon loss rates and actually 2-photon coupling rate than with 4-wave mixing. So the circuit we introduced to realize this is we call it the autoparametric resonator. So you essentially can view it as a squid connected to a resonator, which if you pump in flux at twice the resonator frequency would provide a parametric amplification. So here, instead of pumping at twice the frequency, we connect to this flux mode a resonance which is at twice the memory frequency. So we effectively replace the classical flux pump by a resonator at twice the frequency. And so the memory mode in practice is looking like this common mode between the two stubs going down to down here, and the buffer mode is a simple lambda over two resonator. And in practice, you can see the chip here. So we like it that there is a single line that connects and couples to the buffer mode from the top, and also acts as a flux tunable element. So this is also our flux lines here in green. And at the bottom, you see a transmon that we use to do Wigner tomography. So if we look at the flux dependence of these frequencies, so here in green, you see the buffer frequency as a function of flux, so it varies a lot with flux. And in blue is plotted twice the memory frequency. And you can see that there is a flux, which we call phi QEC, where there is the nice frequency matching condition, so 2 omega memory equal to omega buffer. And so this is a working point where the two-photon loss mechanism will be active, will be turned on. So at that point, unfortunately, we cannot do Wigner tomography because the two-photon loss mechanism inhibits any unitary dynamics such as the one we need for Wigner tomography by Zeno effect. And so we need to move in flux dynamically when we want to do the Wigner tomography. And so we choose this other spot where the frequency matching condition is absolutely not valid to do the Wigner tomography. So in practice, we will switch the flux between these two positions, right? So the QEC position for two-photon loss and the tomography position to do tomography. All right, so let's start using this device, right? So if we first want to just generate a CAD state, the only thing we need to do is turn on the flux at the working point and drive the buffer mode at its resonance frequency for 300 nanoseconds here. And then we do a Wigner tomography by going to the other flux point and so measuring the transmon. And this is the kind of Wigner measurements we can acquire doing so. So indeed, you see that starting from the vacuum and just turning on this single drive, but at the right flux, we managed to get a CAD state. So now if we want to determine what is the two-photon loss rate, we start again from this pulse sequence to prepare a CAD state. But now what we're going to do is turn off the drive on the buffer and keep for some time the two-photon dissipation on, so that the CAD state will get smaller and smaller and eventually go down to the vacuum state. And so here we do this experiment. And by simulating this experiment in QTIP and looking at and feeding the kappa 2 parameter, so this two-photon loss rate, we're able to identify that the two-photon loss rate is a bit above 2 megahertz. And if we compare that to the lifetime of the cavity, which is 11 microseconds, we get a ratio above 100. So with such a large ratio, there are a few things we can do. So before showing you the bit flip time and phase flip rate, so we can, for instance, enhance the Wigner tomography. So Wigner tomography is done. So if you want to measure the Wigner function at amplitude beta, first we need to displace the cavity by minus beta, and then measure the parity of the number of photons. So this is the procedure that was developed by Luterbach-Davidovich and implemented later. So this protocol of measuring the parity, it takes time. So first we have to do pi over 2 pulses on the qubit that are unconditional on the number of photons, which becomes hard if there are many photons. And more importantly, the waiting time during a pi over kappa, during which the qubit gets information about, encodes information about the parity, during that time, you know, if there are a lot of photons, it's likely that a photon will get lost, and so the parity measurement will be wrong. And so what we simply, so this is one Wigner function of a cat using this standard protocol. So what we did instead is simply right before measuring the parity here, we had a step of 300 nanoseconds where we evacuate the pairs of photons down to only 0 or 1 photon in the resonator. And so doing so, we eliminate these issues, and we restore a very nice contrast for the interference fringes. Okay, now, so we can then measure the phase flip rate, so the rate of Z errors, as a function of the number of photons in the cat code. So we expected that this would be linear in a number of photons, and indeed it is linear. So we see no deviation to linearity. So it really obeys the expected law. And now if we measure the bit flip time, so the duration between two X errors as a function of number of photons, we indeed start to getting an exponential rise. So this time it's not linear, right? So we indeed get a very sharp rise in bit flip time. And at some point it starts to somehow saturate, and we went up to 0.3 seconds. So this is already very nice, but we were expecting better, right? So how do we understand the deviation to what we expected? So first, what we exactly expected was this black line. So exponential 2 alpha squared divided essentially by the pure dephasing rate times alpha squared. This is something we measure, and so we would expect the bit flip time to match this black line. So what happens actually is that the two photon exchange rate is so large that the buffer loss rate into the environment is not strong enough to evacuate the photons at the right pace. So in fact, our adiabatic approximation, adiabatic elimination of the buffer mode does not exactly work. And so if we take that into account, take into account the fact that there are coherent exchanges between buffer and memory instead of just buffer exiting, right? So we get this blue line, which reproduces our measurement. But then we still have this saturation, and unfortunately this saturation we attribute to the excitation of Chance-Mond higher states, which we also measure. And that puts a cap at these red dots, right? So we think we understand that the Chance-Mond is again a big issue here, and the fact that we populate these higher states seem to limit our bit flip times. So here I advertise the work of the group of Zaki Lertas and my colleagues at Alice and Bob, who did experiments with 4-wave mixing, but without the Chance-Mond. And we were able to go up to 15 seconds while preserving the coherences. And so finally, I'd like to show you how to do gates on this experiment. So if we want to do a Z gate, so starting from a cat state like this one, so on the equator of the logical block sphere, if we want to do a Z gate, we just drive the memory at its resonance frequency. And what's going to happen is that the interference fringes will simply shift as a function of time. That corresponds really to a Z rotation. So if we now look at the Wigner function at 0 as a function of time, we see decaying oscillations like this, and that corresponds to a 96.5% fidelity for the Z gate. And if we want to do X gate, so I'm running a bit late, I'm going to be fast, but this one was a very nice proposal by Victor Albert and others at Yale. And so starting from a coherence state alpha, if we want to do this X gate, we first stop smoothly the drive on the buffer, so that the state will go down in the 0-1 manifold, and then turn it on again, but with a different phase. And the phase at which you turn it on will actually be the angle of the X rotation. So let me show you how that works experimentally. So here we're in the 0-1 manifold, and then we pump again, and up you see the coherent state is transformed into a cat state. So if we now rotate it in the, with the right phase, this is the X gate at any angle on the right. So we here do it's simply a Rabi oscillation in the logical basis. So the fidelity is not great; it's 80%, but it could get improved with better numbers, right? All right, so that's it, right? So there's the autoparametric cat, which has very promising behavior for the bit flip time as a function of number of photons, and we can do gates, right? So, and I like to thank people who did it. So Antoine Marquet did all the experiments in Lyon, and with the help of many others, and the idea of the autoparametric cat came from Raphaël Lescan at Alice and Bob. Okay, thank you.
Okay, we have time for 2 or 3 questions.
Hi, thanks for the great talk. So it's a really cool idea, but because you don't have a parametric control to turn on this interaction, you sort of have a trade-off between the per cell limit placed by the buffer mode on the memory mode, if you wanted to evacuate the buffer faster.
So I'm sorry, but there's a lot of...
Sorry, so if you want to evacuate the buffer faster, you'll eventually have a per cell limit on the memory mode from the buffer mode. Is it possible to do some sort of per cell filtering there? Because you don't want to trade off between your 2-photon dissipation and single photon dissipation.
Yeah, that's a great question. So in fact, we kind of have a protection against the memory evacuation. So it's a subtle thing, but you see that the input port on the buffer is actually not put at the symmetrical point, right? It's displaced. And this is a trick, actually, which is such that at that particular point, this input line drives the buffer and so couples very well to the buffer, but does not couple to the memory mode. Because, in fact, there's some kind of interference between the differential and common mode of this transmission line. And so we can choose the buffer, the coupling rate to the buffer, by the position of the last wire bond on that line. So actually, we, according to our simulations, if we remove 2 more wire bonds, the buffer rate will improve, but the per cell protection will even improve as well so it's a win-win situation. Yeah.
Okay, is there one more short question? Yeah, we all want coffee, yeah? Here's a quick one, okay.
Yeah, really impressive work. I wanted to ask about the last sort of part where you showed the X gate, that if you ramp down the coupling, does that mean that your protection is also to some extent getting weaker or do you get the kappa 2 down when you do the X gate, or did I understand somehow incorrectly? So your sort of, your sort of protection, you were making the claim that you want kappa 2 or kappa 1 to be very large, right? But now you're saying that you are somehow in this gate you are changing the kappa 2. So is your protection then going to be a little bit weaker here during the gate?
Yes. So indeed, for the X gate, so kappa 2 stays fixed actually. You see, because we stay at the working point. But indeed, we leave. So we diminish the number of photons, and so effectively we lose the noise bias when we go down. So yes. So this gate indeed does not benefit during the whole trajectory of the noise bias. It's yes, but so this is indeed that's an issue, but yes, anyway, when you do a next gate, right, you go from you map X for Z, right? So in the end, if the Z errors were protected, but not if the X errors were protected, but not the Z ones, then you change that anyway, right? So it's a bit unavoidable, I would say.
Okay. Let's thank Benjamin and all speakers in this session this morning. Thank you very much. Okay, so now we have a coffee break, and I was told that we can take the full 20 minutes. So that means we'll reconvene here, let's call it 11:10. Okay, thank you.
want. It's already on. They will, if you start speaking.
Okay. All right. Hello. Okay. Welcome back to the second session of the day on unconventional superconducting qubits. My name is Rajamani Vijayaraghavan, or Vijay, for those who don't want to play the tongue twister game. And I am an associate professor at the Tata Institute of Fundamental Research in Mumbai, and I also work on superconducting qubits. I guess, Stefan, are we ready to go? Okay, great. So let me introduce our first speaker, Angela Koo from University of Illinois, Urbana-Champaign. And she's going to be telling us about coupling her unconventional Andreev qubit to a regular superconducting qubit. Over to you, Angela.
Okay. Right. Okay, so I've been asked to stay at this stand, and I will do that. Okay, so thank you to the organizers for organizing this conference. It's been really cool to see all the products and the results that everyone has shown so far. So today I'm really happy to be able to discuss with you some of our, I may move around and my voice may start to decrease as I do that, so just like someone give me a sign if I'm too far away from the mic. Okay, so today I'd like to share with you our work coupling an Andreev spin qubit to a transmon. This work was actually mostly done at Delft, and so and done by Marta and Arno, the grad students on it, who of course do all the work of our experiments. So the first question I want to ask is, how should we build a quantum computer? And I guess I should say that obviously we're going to build it out of superconducting qubits, but the question is, how should we actually do that? So we can think of two possible ways, maybe there are many more, but two possible ways we can split it up. So we can imagine that, let me actually put a laser pointer on this so I can actually point. Can I make it green? No, okay. Then we'll just have a red laser pointer. Okay, so one way we can build a quantum computer is to imagine that you have some single physical platform that is useful for both memory and processing. So we build this amazing platform, perhaps out of superconducting qubits, that is both able to serve as a memory, which we want to keep very well isolated from the environment, but also as useful for processing, where we are able to access it and perform gates. But this is kind of a difficult ask, right? Because we need to satisfy kind of conflicting requirements of both having it be a memory and a processor. So it's difficult to satisfy all the possible tasks for using a single platform. You could also consider another possibility where we actually look at multiple different platforms that are specialized for each purpose. So we can think of taking a page out of our current computers and imagining that we have some kind of platform that we use for memory, some kind of platform that we use for processing, fast processing or slow processing, and some fast memory. And this might be a different physical platform for each kind. And then so we release some of these requirements of forcing the platform to both be memory and processing, but then we still have another difficulty in this case, so where the interconnects become challenging to build. So if we choose the second path, do we get rid of kind of the benefits of using these different specialized physical platforms by having to build these interconnects? And I don't know which one of these is the best way of building a quantum computer, but I'm going to focus on the second path for now, and then we'll see how things go. So two possible different physical platforms that we want to put together are spin qubits and superconducting qubits. So spin qubits have the benefit of being very compact, so you can have multiple of them on, you can have many of them in a very small space, and they typically have pretty long lifetimes, so we think that they might be good as a memory. For superconducting qubits, I don't really need to talk about the benefits here for superconducting qubits, but we have some, you can get really high fidelity operations, and it's very easy to remotely couple them. And so we can think of this as maybe being good as a manipulation qubit, good for doing processing. And the difficulty with coupling spin qubits to superconducting qubits is actually typically they're very different in size. So spin qubits can be really small, while superconducting qubits are typically fairly big. So angstroms up to millimeters, and also they can be based on different kind of physics. So a spin qubit is based on kind of magnetic fields, and superconducting qubits don't necessarily have to be based on magnetic fields. But there is a platform that's quite easy to couple to, easy-ish, to couple to superconducting resonators, and that is the platform of Andreev spin qubits. These have been coupled to superconducting resonators, and I'll discuss a little bit the unconventional Andreev spin qubit that one couples to a superconducting resonator. So the question is, what is an Andreev spin qubit? And the idea here is that you can get a superconducting junction, so you can think of a particle in a box, where the energy levels are determined by these particles that are bouncing back and forth. And because we have superconducting boundary conditions, the particle that's bouncing back and forth is a quasi-particle that's composed of a superposition of an electron and a hole. And this, so this quasi-particle has a well-defined spin, and so the energy levels is going to look as shown here on the right. Yeah, okay, cool. As shown here on the right, and what we want to use as our qubit, our 2 qubit states, are the quasi-particle spin down and the quasi-particle spin up. And if you have some spin-orbit coupling in your system, that breaks the degeneracy between spin down and spin up, so you get a little bit of an energy level spacing. And then you can also, from the spin-orbit coupling, the current that passes through your superconducting junction is going to, the direction of the current actually reflects the state of your spin, whether it's spin down or spin up. And then so what we can do is what we typically do in superconducting circuits. We can couple it, and this was done by the Deveray group and then also by the Saclay group, where you can couple your Josephson junction into a loop and then couple that to a resonator. And then so if it's coupled to a resonator and you monitor the phase of that resonator, depending on the direction of current flow, the response of your resonator is going to change, and then you can read out and manipulate your Andreev spin qubit. And so here's the response of the resonator for being in the ground state or being in the different spin states. So this is an amazing implementation. It was Max Hayes, who was the lead author of this group, was able to couple the Andreev spin qubit to a resonator. But this implementation does have a couple of drawbacks. So the kind of 2 issues are that your gate operations are via Raman processes, and this can be slow. So you can't do, in this implementation, there was no direct drive between the spin up and the spin down. Oops, sorry. And the qubit states are actually excited states. So if you look actually at this diagram that shows you the state of the qubit, qubit mostly lives in a ground state that's not the eigenstate, that's not the qubit states that we want to use, or the states that we want to use are these 2 different spin states, and it doesn't usually live in this space. So there's a lot of leakage out of your qubit subspace, and you also have initialization problems because you need to get into this excited state you need to get into this excited state to initialize your qubit. And then so the way that you can get around this, you can actually solve this problem of at least the qubit states being the excited states, is actually to change your platform a little bit. So instead of just having a junction, you can isolate your spin from your leads a little bit more by creating a quantum dot in the center. And by creating a quantum dot, what that does is it creates some charging energy, and then given that charging energy, given that charging energy, what happens is that the energy spacing between the ground state and the excited states of the system are determined by both this charging energy and also the level spacing of your quantum dot. And then so originally where you had a system where your spin states are your excited states of the system, as located here, this is what we're going to call the singlet state. You can tune the energy by changing the coupling between your quantum dot and your superconducting leads to make it so that your spin states become the ground states of the system. And then so if your spin states become the ground states of your system, you get rid of this problem of the qubit states being your excited states and having these leakage issues. And then so we'd like to try to implement an Andreev spin qubit by making the center part of our junction into a quantum dot. And then so how we do that is by coupling the spin quantum dot spin system to a transmon. And so a transmon forms kind of this part. We incorporate the superconductor quantum dot superconductor junction with the standard junction in a squid geometry. And then so we have a standard Josephson junction coupled to shunted by a large capacitor, so that forms the transmon part. And then you get an additional contribution to your system from the S quantum dot S system, which is shown here. And then if you're in the singlet state, so that's the state that we don't want to be in, where our Andreev spin qubit is in the excited state subspace of the system, then you'll have your standard contribution to the potential of a squid, where you have a cosine phi. If you're in the doublet state, which is what we do want, where our spin states now become the ground state of the system, and we can get rid of this leakage problem, then your contribution to the potential has a cosine phi minus pi. And then so what we can do is actually monitor the frequency of the transmon, and we'll use the transmon mostly here for readout of our Andreev spin qubit. So if we look at how the potential changes, if you're in the singlet state, you have 0 at 5 phase difference across this junction. And if we sum it with the potential due to this Josephson junction here, they're both 0 at 0 phase. And then so you end up with a deeper potential, and your transmon frequency will be larger. So that's the standard cosine phi. And then if you have a doublet state, so where we get this cosine phi minus pi, the well will become shallower, and then so your transmon frequency will become lower. And then so by looking at the transmon frequency, we can actually read out our device. And then so what the device actually looks like, I am seriously running out of time. Okay, so what the device actually looks like is that it has a aluminum nanowire that is, indium arsenide nanowires that is proximatized by aluminum, and you can etch junctions. And you can etch a junction that forms just our Josephson junction, and then our S quantum dot S junction has a bunch of gates, has gates under it that form that quantum dot, so that isolate it from the environment. And then what we can do is we can perform two-tone spectroscopy to monitor our device as a function of changing this plunger gate. And what that plunger gate is going to do is going to be able to move us from the singlet phase to this doublet phase. And then if we look at the transmon frequency as we're moving our plunger gate, then what we see is that if we're at phi external is equal to 0, so there we have a cosine phi for the singlet and cosine phi minus pi for the doublet, our frequency is, as we move this plunger gate, suddenly drops and then comes back. And if we look at the same, if we perform the same experiment at phi external is equal to pi, so now the roles are reversed for the doublet state and the singlet state. The transmon frequency is lower in the same place where it was higher at phi equals 0, and the doublet state, here the frequency is higher where it was lower before. And then so we can confirm our interpretation where we're actually tuning our ground state of the system by changing this plunger gate from the singlet state to the doublet state, which is the state that we want to live in, by looking at the phase dependence of our transmon frequency. And then so if we're sitting in the singlet state, you have this cosine phi behavior, which is standard for the junction. So we're in the singlet state. And then if we change our plunger gate, we get this cosine phi minus pi. So we're able to tune between the singlet and the doublet state to get rid of this problem of leakage by changing our plunger gate. And then so we can get rid of this leakage issue. And so that solves one problem with this first implementation. The next thing we can do is see if we can help with also making the gate operations a little bit faster. And then so the way that we do that is that we now start to consider this spin-orbit coupling. So we can tune ourselves into this doublet state, and our doublet state can now split into 2 states. So these are going to be our 2 different spin states, and we can park ourselves at a specific flux, and by doing that, then we can address our Andreev spin qubit and cause transitions between the ground state to the down state of the spin to the up state of the spin. And then our level diagram now with the transmon included is going to look something like this. So we have our transmon state for the Andreev spin state being in the down state, and then the transmon transition for the Andreev spin state being in the up state. And then so what we're going to do is now look at our transmon frequency and within this framework. And then so if we look at our transmon frequency for tuning ourselves into being in either the doublet state or the singlet state, we see that we can look at the transmon frequency. When we're in the singlet state, there's only 1 manifold. If we're in the doublet state where we have 2 different spin species, so that form our spin qubit, then we have 2 different transmon frequencies. And then what we can do is apply a magnetic field now to change the splitting between the two different spin states. So that the spin states determine the potential of our transmon. So if they're split at smaller frequencies, then you're going to have some occupation in the lower spin state and less occupation in the higher spin state, which is shown here. And then as you tune the frequency more and more so that the spin states become farther and farther separated in frequency, then most of the population is going to live in this ground state, and then the visibility of this transition is going to decrease for being in the higher spin state. And then so now we know we can tune the different spin states of our system. So we can try to perform direct drives between the Andreev spin state, and we can look at this direct driving as a function of the external flux, and it has the expected flux dependence, and we can also look at the frequency as a function of the applied magnetic field. So because these are spin states, I can just apply a magnetic field to make that splitting larger. And then now I can try to perform Rabi oscillations between these different spin states. And so this is the Rabi oscillations as a function of the width of our pulse and the amplitude of the pulse. And what we see is that the amplitude of our Rabi oscillations, the frequency of our Rabi oscillations increases with increasing amplitude of the drive, and you can get Rabi oscillations that are extremely fast on the order of 300 megahertz. And so if we do this, if we can perform Rabi oscillations, then we can measure the spin qubit lifetimes. And then so the lifetimes are, the T1 is on the order of 24 microseconds. The T2s are quite short, and they do get a little bit longer by performing dynamical decoupling, but they're still quite short. But I do want to emphasize that we've, in this kind of system, increased the, we've been able to get rid of the problem of leakage and initialization while also driving much faster. And we still maintain the same lifetimes and coherence time as were possible in previous implementations of the qubit. So we've added better control of the system without kind of decreasing the coherence times of the device. And when we know where this kind of the limitations on the lifetimes are coming from, there's a very large nuclear spin in indium arsenide. So if you implement a system, if you implement the Andreev spin qubit in a material that has a lower nuclear spin, we expect the coherence times to become much larger. Okay, I think I really am super out of time. So I'm going to just skip this slide and say that we built an Andreev spin qubit from a superconductor quantum dot superconductor system. We demonstrated direct Rabi driving, and if you want more details, you can look at these 3 papers. And just again to acknowledge, so Arna and Marta really spearheaded the work, and this work was co-supervised by Christian and Bernard, shown here. Okay, so thank you for your attention, and I'm happy to take any questions.
Okay, I think we have time for maybe 1 or 2 quick questions. Yeah.
Exciting results. How about the charge noise? Because now you have the gates, and do you think about, maybe it's not limiting you now, but is there going to be possible issues with that?
Yeah, so let me stand here again, sorry. So the question was whether charge noises will limit us in the future, and I think that because in the quantum dot there are actually multiple places in which you can tune to being in the doublet, being the ground state of the system, we can find sweet spots in the gate so that the charge noise is affecting us less.
My question is about the non-nuclear spin. So what do you envision? Do you envision, say, silicon or?
Yeah, so proximatizing silicon is really, really difficult. But I think germanium is a good option. There the spin is low, and it becomes much easier to proximatize.
Okay, let's thank Angela again.
Okay.
The next speaker is Barkay Guttel from Weizmann Institute, and he's going to be telling us about a superconducting cavity with tens of milliseconds single photon coherence time. Over to you. You have 20 minutes.
Thank you. So as you said, my name is Barkay. I'm from the Weizmann Institute in Israel, and this work was done, and we showed that our superconducting cavity qubit is able to encode qubit for tens of milliseconds single photon coherence time, and I will tell you how. So first of all, the motivation behind our work is this plot. Here we can see the coherence time and the lifetimes of superconducting qubits of different architectures, and we see the exponential increase over the years. But we also see that at some point it kind of stagnated at 2 milliseconds at about 2016. Also, this work was done with another superconducting cavity. And in this work, we basically try to put the next data point, which we did, at 34 milliseconds coherence time of a qubit encoded in a superconducting cavity. So let me give you a bit of introduction, although Patrick did a pretty good job this morning. So why we want to use superconducting cavities? Because they have two main advantages. First of all, they have high quality factors, so naturally the lifetimes of the qubit encoded in them is going to be longer. And secondly, like Benjamin talked about, we can encode cat states or other bosonic modes, and we can use this harmonic oscillator feature of many states, and we can do quantum error correction even with a single element. So in this sense, it's a hardware efficient way to do quantum error correction, where you don't need as many physical qubits. On the right, you see one geometry of superconducting cavity. They can come in different shapes, and as I will show later. But you also need to take into account that we need to introduce some nonlinearity into the system. Otherwise, you won't be able to encode quantum information in it. In our case, we do it with this transmon that we couple to the cavity. This transmon is a nonlinear element, and we use it to encode and decode the information from the superconducting cavity. However, keep in mind that the information is stored in the cavity and not in the transmon. The transmon is only used for gates, encoding, decoding, and that kind of stuff, but the information itself is stored in the superconducting cavity. So without further ado, let me introduce you to our oh, sorry, I need to talk about decoherence channel in cavity qubits. So decoherence channels, we have three main decoherence channels, and these decoherence channels is what limited us so far to 2 milliseconds, and what we needed to overcome in order to get to tens of milliseconds coherence time. So the first decoherence channel is just the surface. So the cavity itself might be perfect, but its surface is not. It's going to have some contaminants on it. It's going to have some oxide layers on it. And these are going to limit the quality factor of the cavity. Secondly, the chip itself. As I said, we need to introduce this transmon on a chip into our cavity, and the chip is not going to be perfect, and the lifetime of the transmon is going to be much lower than that of the cavity. So this will cause the inverse Parcel effect and also limit the lifetime of the superconducting cavity. And lastly, when the transmon is excited, it kind of reads the quantum information that is stored in the cavity. And this will cause dephasing of the cavity and will limit its coherence time. All of these channels together have what limited us so far to about 2 milliseconds. And what we want is to try to mitigate them and then get our coherence time to much longer times. So now, without further ado, let me introduce you to our cavity. Here you see a 3D rendering of the entire thing, and here I have a 3D printed version, so if you want to have a closer look, please by all means approach after the talk. And I mainly want to focus on the two main parts, not on all the flanges and screws. So one part, of course, is the cavity itself. It is made out of two niobium parts that are electron beam welded together. We use this method because this is the best method that you can weld two niobium parts, and this causes the seam to be almost lossless. And in the red, you see a depiction of the energy that is stored in the cavity. And the next part is also the ancilla chip. So on this ancilla chip, you can see the transmon that we use to encode and decode the quantum information from the cavity. This specific geometry is half elliptical. We like to call it mushroom cavity, and it has two main advantages. First of all, it limits the energy participation ratio on the surface. Like I said, the surface is a weak point of the cavity, so we want the energy to be stored in the vacuum and not on the surface. This geometry is perfect for that. And secondly, it allows us to only introduce the chip by 1 millimeter or so, and so it will limit the losses that come from the chip and from the transmon that is on it. So these are the two advantages of this design. And once we had this design, we sent it for fabrication. And once we had our cavity, we wanted to measure it and characterize the cavity on its own. So once we had the cavity, still without the transmon, we put it into this chemical etching process called BCP, and this makes the surface of the cavity to be smoother. So you see that it started a bit edgy, and then after this process, it becomes smoother. This also reduces the energy participation ratio on the surface. And then we mounted our cavity into the fridge, we cooled it down, we measured its lifetime, and we got these results. So 110 milliseconds lifetime for the field. However, like I said, it's a field. There is no transmon there, so there is no quantum information yet. This is only classical field, and it's just to show that our cavity is pretty good on its own. However, after some time, we saw this degradation. Sorry about the plot, it's kind of moved, but the degradation shows that we got to 30 milliseconds after some cooldown cycles. The mechanism of the degradation is still under investigation. If you want to discuss it, I will be happy to do it after the talk. But keep in mind that throughout the next slides, the cavity was in this state. So the state where it has 30 milliseconds lifetime. Then the next part was to actually introduce the transmon into the cavity, and this way we can encode quantum information. Here you can see all the parameters of the system, but I want us to take a quick look on the two main parameters. First of all, the thermal population. We cooled down the cavity with the transmon, not with ice cubes and penguins, but we did similar things, and we limited the thermal population to about 0.1%. This means that the transmon is excited on average every 92 milliseconds, which means this is what we can hope to achieve as a dephasing time of the cavity. Secondly, the coupling between the transmon and the cavity is very weak. So the dispersive coupling is 42 kilohertz, and this means that we will not be limited by the inverse Parcel effect, where we put the limit to about almost 300 milliseconds. So this also will not limit us. However, you might ask, okay, if the coupling is so weak, how can you actually encode information fast enough? And for that, we use this sideband drive when we exchange two excitations in the transmon into a single excitation in the cavity. This way, we can encode a single photon state in about 1 microsecond, which is 10 times faster than what is imposed by the dispersive coupling alone. Okay, so now that we have our system in the fridge, we know how to encode single photon states. The next point was to actually measure the lifetime and the coherence time of single photon states. And indeed, we see these great results, I think, 25.6 milliseconds lifetime and 34 milliseconds coherence time. We can also take it to the next step and think of what's limiting us even more. And we can already say that we are mostly limited, the coherence time is mostly limited by 2 times T1 and a bit limited by the dephasing time because of transmon heating. So like I said before, 0.1% might not be enough. And we can also say a bit more about the system when we put lower bounds on the intrinsic dephasing time of the cavity and the heating time of the cavity, both in orders of seconds. This means that we can use this cavity in the future to do experiments on other decoherence channels or quantum sensing that so far have been really difficult to do. And in this seconds order of times, we can actually do that. And lastly, for the experimentalists in the crowd that think, oh my God, the lifetime is so long, it must have taken them forever to wait between experiments and do the averaging, we use this active exchange of energy between the cavity and the lossy readout, and that way we could empty the cavity within about 2 milliseconds and get a good rate of doing experiments in our system. Okay, so far we talked about the single photon encoding, how we can encode, we can use it as a quantum memory, for example, and it gets to tens of milliseconds. But as I said in the beginning, superconducting cavities are very good for their bosonic nature. We can do bosonic quantum error correction with them. So the next thing we wanted to show is to show the potential of this cavity for multi-photon states like GKP, if you know it, or cat states like Benjamin was talking about. And this is exactly the next step that we took. We wanted to encode a cat state. Here we see a simulation of a cat state, which is just a superposition of 2 coherent states. And we we define the size of the cat state as the distance, or the square root of the size, as the distance between the coherent state. If the size is larger, it means that the code words in our code space will be more separate, and the quantum error correction will be better and better. However, trying to plot this plot for big cat states, like the entire Wigner tomography, will take forever. So in order to actually characterize a cat state, we are only looking at the fringes at the center. If you look at the fringes, you can look at the oscillation frequency, and according to that, you can know what is the size of the cat state. So we did exactly that, and the biggest cat state that we could encode has a size of 1,024 photons, which is, again, over an order of magnitude improvement compared to previous demonstrations. We call this cat state a chunk state because it's quite fat, not to be, But OK, so this is a cat state that can definitely be used for quantum error correction in the future. And the last part of characterization that we wanted to do is to show what is the time where it dephase again. Again, like Benjamin said, we have the bit flip times, but we also have the phase flip times. So we wanted to measure how much time it keeps its nice coherence and don't lose it. So this we can see here. This is a cat state, a smaller cat state with 200 photons, just as an example, and we can follow this exponential decay, and then we can say, OK, this cat state has a decoherence rate of 222 microseconds. We repeat it for many sizes of cats, and we can see this linear dependence, as expected, on the size of the cat. We also see that in the denominator, we have this 2 times the lifetime of the cavity, and this indicates that you have to have good lifetime of the cavity if you want to encode big cat states. Otherwise, your cat state will just diminish without you having any possibility to measure it or to do anything with it. Specifically for the chunk state that we shown before, with 1,024 photons, the decoherence time is 54 microseconds, which is great because it's much longer than achievable gate time, which we put at around 1 microsecond. So just to summarize this, we've shown that our cavity is not only good for single photon states as a quantum memory, it can definitely be used for bosonic quantum error correction, where we use all the harmonic oscillator features and all the states and encode these kind of states as well. Let me just conclude. We use this novel geometry for our niobium cavity when we have 2 parts that we weld together. We showed that a single photon lifetime was 25.6 milliseconds, and the coherence time was 34 milliseconds. Then we can definitely say that we can further improve on these results. We can put our cavity in a baking oven, and this way we remove all the oxides from it, and this will also increase the quality factor, and we will be able to increase the lifetime. We can also use this real-time ancilla error mitigation, where we push every time the transmon is getting to the excitant state, we can push it down actively, and that way we will also increase the dephasing time. This is a work that we're actually working on right now, and I hope we will be able to publish something on arXiv in the next couple of months. And lastly, this cavity can be used for many different directions, like I mentioned, quantum sensing or decoherent channels, but it can also be used for bosonic quantum error correction, as I show here a couple of plots that show you cat states with more than 2 legs or 4 legs or stuff like that, that can definitely be used for bosonic quantum error correction in the future. And that's it. If you have any questions or you want to have a look at the cavity, please come and look for me.
We have time for questions. Okay, over there.
Hey, great talk. So I'm curious why you decided to go for dispersive control and not like echoed conditional displacement kind of control.
Could you repeat it?
Sorry, I'm curious. So you have an ancilla which is sort of decoupled from the cavity or undercoupled to the cavity. So I'm curious why you didn't go for like a loci regime and do some sort of conditional displacement kind of control instead of dispersive interactions.
So instead of dispersive interactions?
Instead of dispersive, the regular dispersive control?
You mean like putting them not in the dispersive regime, but like closer together?
We can maybe, there's a longer question, so we can just chat about it later.
Yeah, for sure. Sorry.
Thanks.
Okay, was there a question over there?
Hi, here. So you said you build it using the E-beam, the building of the cavity. Can you hear me? Yeah. So I'm talking about the welding of the cavity. Have you seen how much of the surface distortion is there, and like what order of surface irregularities are there? Is it of the order of microns, or when you weld it?
Yeah. So the surface, we have two indications of basically how much of the energy is in the surface. First of all, like I said, we have the energy participation ratio, also called the fill-in factor, where you can think about it as you have an oxide layer on your surface that has, I don't know, 3 nanometers, 10 nanometers thickness. And the more thickness it has and the more your energy is concentrated on the surface, the lower your quality factor is going to be. Because superconductors are perfect, but oxides obviously are not. So this is one thing. More than that, you can also think about the residual resistance. So every RF cavity, even though superconductors are perfect at DC, they're not in RF. So you still have this residual resistance, and this will also cause, because of the currents on the surface, this will also cause some limitation. In our case, it's the fill-in factor, so the energy that is stored in the oxides, that's limiting us more. At least this is what we suspect, and this is why we want to maybe bake it in the future and remove the oxides in a better way.
Okay, maybe one more question. Okay, yeah.
You said that it was E-beam welding. Why not laser welding? Can you comment on the method?
Oh, electron beam welding. Electron beam welding is, you can do welding in many different ways. So the easiest one we can also see, like you just put like a torch or something. Then you can do laser welding, which is better. And electron beam welding, it's kind of like fabrication. Electrons are the nicest way to do that, because it gets you the best seam between the two parts. So this specific method, and actually this cavity is inspired by cavities that were used for particle accelerators, because basically they have the best cavities in the world. So electron beam as well, this is how they make these cavities, when they weld sheets of niobium or bulks of a niobium.
Okay, let's thank the speaker again. The next talk is by Vasilii Vadimov from Aalto University. He's going to be telling us about resonator-free readout of a transmon qubit.
Thank you and welcome. It's a great pleasure to give a talk here at this wonderful conference. My talk is about a resonator-free readout of a Unimond qubit. It's a theory talk. The outline is the following. First, I introduce the Unimond qubit, which is a recently developed qubit, and discuss how it can be, discuss its mode structure, and present a way how to provide a readout. Then the readout is calculated using developed input-output theories for superconducting circuits. I'm going to briefly introduce it. I unfortunately don't have much time to dive into details. And then followed by results and some parameters fine-tuning. And also, they're going to be a poster by Suman Kundu on experimental results of the setup which we propose. So, Unimond qubit is a grounded lambda over 2 coplanar waveguide resonator, where the central conductor is interrupted by a Josephson junction. So there are 2 loops of the Unimond, here and here, and the junction is biased by the difference of the magnetic fluxes of 2 loops. So this provides some protection against the flux noise if the loops are gradiometric, so it's sensitive only to magnetic field gradients, not to magnetic field, homogeneous magnetic field itself. So last year there was a paper published on the Unimon, and here you can see the false color image of the sample. You can identify 3 Unimons. They're blue. And right there is a flux dispersion picture. So there are sweet spots at 0 flux quantum and half flux quantum, and the latter is an operating point of the Unimon, where it gets the highest harmonicity and reaches 400 megahertz, which is higher than Transmon. The easiest lumped element model which describes the physics of Unimons is given on the slide, and it's basically just a capacitor in parallel with Josephson junction and inductor. Its Hamiltonian is quite simple, and at half-flux quantum bias, the Josephson junction acts as a negative nonlinear inductor. That's why it partially cancels the quadratic potential of inductance, and harmonicity becomes more pronounced. And the energy levels are shown in the slide, and this has positive harmonicity. The frequency scale and harmonicity are comparable to ones of Transmon, so it can operate it similarly. But can we have advantage out of Unimon? And the answer is yes. The key difference from the between the Unimon and Transmon is that Unimon is essentially multimode. So here I show the mode structure of the CPW, pure CPW without the junction. The blue mode is a fundamental mode. It has 0 current in the middle, so if we place a junction there, it's not going to be affected at all. It remains linear and decoupled from the rest. But say the second mode, which is purple here, it has current maximum, so it's going to be strongly affected by the junction and contributes to the qubit mode. So that's the idea. Why don't we introduce some small coupling between linear and qubit mode in such a way that we can use linear mode as a readout mode for our dispersive readout technique. And this coupling can be introduced by slightly shifting junction away from the middle point. The minimal model which has the desired physics is shown at the bottom of the slide. It consists of 2 LC circuits coupled to the junction. And there are 2 modes. If this circuit is symmetric, in-phase mode, which is perfectly linear, and which you call readout mode, and the nonlinear mode where the voltage oscillates in counterphase, that's going to be nonlinear qubit mode. And if we introduce a little bit of a symmetry between the LC circuits, then we can couple them. So here there is some results for the flux spectrum and dispersive shift of this kind of circuit. So we give some slight asymmetry and study single photon excitations, the frequency of the single photon excitations as a function of flux. So here we see the qubit mode, which is strongly flux dispersive in almost flat readout mode and anti-crossing between them. And this is going to be our operating sweet spot of the Unimon. And on the right side, there is a dispersive shift as a function of a symmetry between the LC circuits. But in order to provide readout, we need to couple this device to a transmission line. And it's better to have preferable coupling to the readout mode and affect the qubit mode as little as possible. So we introduced these 2-point couplers. There are 2 coupling capacitors to couple to the 50-ohm transmission line. And that way, we couple mostly to the readout mode. And to study such a circuit, we employ input-output theory developed for circuits. And I'm going to say a bit about the theory itself. So the idea is to provide an I/O theory for nonlinear circuits free of Markovian and rotative wave approximations. So there are some key properties of it. The main points are that it's developed in principle for arbitrary circuits, and it allows only the only quantity it gives access to is basically the output field. It doesn't provide information about the state of the system itself, so it acts some kind of black box framework. It started from the classical Langevin equation for classical Kirchhoff's law for superconducting circuits. Here it's shown, for example, here. And further, I employ careless formalism for dissipative circuit and deal with influence functional to resolve it into some many-body Liouville-like equation, which I can solve later. So now we are ready to go to see results. First, I study the transmission coefficient for such a circuit. Here it's shown, its absolute value is shown on the figure. There is a very strong feature at the frequency of the readout mode is here, and also some weak feature at the frequency of the qubit transition, slightly below 5 gigahertz. So in the bottom there are frequencies of these transitions and also their line widths. Also, there is some small peak around here, which corresponds to FH transition. That comes probably from some numerical artifacts and not perfect numerical scheme. And that has been done for low temperature, 10 milli-K, where the qubit is not populated. What we're going to do next is to heat it up and give some population. And then we see 2 more peaks appearing. They're quite strong. The reason we don't see higher peaks because I cut my Hilbert space of the Unemann with 4 levels. And also we can see here on this zoom in of this peak that there are slight bumps which correspond to dispersive shift. In addition, we see that there is pure dephasing. The line width of the qubit transition increases by a factor of 50. So next step would be to do single-shot readout, simulate single-shot readout. And instead of preparation of the qubit in some state and doing sending readout pulse and accumulating the signal, I consider a thermally populated qubit with under monochromatic drive of the resonant. But I average the signal over the finite time interval, 3.5 microseconds. And this is, I get the signal, and this is a probability of observation, this in phase and quarter phase quadratures, normalized by the voltage drive, shown here. And we see several spots which correspond to different qubit states. But on top of that, we see these straight lines which correspond to different transitions. For example, this is GE, EF, and FH is not visible. On top of that, we see something weird here, which is probably coming also from some numerical artifacts. So here, so far, we consider symmetric coupling, coupling capacitors 3 femtofarad each. But is that optimal? Because there is some inherent asymmetry of the circuit itself. So we can try to fine-tune it to suppress their EG transition of the qubit to avoid partial decay. And it turns out for this circuit shown before, it is possible to suppress this transition up to numerical accuracy completely, which never going to happen in real life, because we also always have some losses in the circuits, dielectric losses or any source of losses, other source of losses. So I introduce resistive shunts to the LC circuits with quite high resistance to simulate the lossy LC circuits. And here I study dependence of the line width of qubit transition as function of asymmetry between the coupling capacitors. And it clearly has a minimum, and it certainly doesn't correspond to a symmetric point. And for these parameters, it corresponds to lifetime of the qubit 188 microseconds, which is quite high. The question is, how robust is this optimal coupling? The most fluctuating parameter in fabrication, the most problematic part of fabrication is fabrication of Josephson junctions. It can deviate a bit higher than other parameters from design. So I consider coupling capacitance to be optimized for Josephson junction here, 13.1 gigahertz, and I change it by 10%, either way, even a bit higher or a bit lower. And it appears that the qubit lifetime, the line width of the qubit transition, it changes only marginally, and T1 decreases, but decreases only a little bit. And here I can come to my conclusions that we show that the multimode nature of the Unimon allows to implement dispersive readout without a separate introduction of the separate readout resonator, and we demonstrate the possibility of the single-shot readout of the Unimon. And by fine-tuning of the coupling capacitors, we can suppress additionally the decay of the qubit state. Again, let me advertise a poster by Suman, and thank you for attention.
Thank you. We have time for questions.
Hi, great talk. Can I ask a more broad question about your input-output theory technique? Does it, or can you obtain a series of equations that can be analytically solved using this technique, or do you have to solve them numerically?
I have to solve it numerically because in the end, it's some many-body quantum problem, which is really difficult to solve analytically. Hopefully, we're going to have preprint in a couple of months in archive, and you can familiarize yourself.
Great, thanks.
Any other questions? So I have one question. So in the last part, you talked about the challenge of exciting the readout mode, which is the symmetric mode, without exciting the qubit.
Yes.
And you showed that, at least from the point of view of Purcell protection, a small asymmetry is manageable, right? That's the thing. But what about readout-induced back action? Have you looked at what would happen if you put sufficient number of photons into your cavity and see if that causes excitations in the qubit space? Because your qubit and readout detuning is similar to typical transmon experiments, right?
It is similar. I didn't study it specifically because I rather, for finite drive, I focused mostly on kind of illustrative part that readout is principle possible. But I think that's going to be for future studies.
Yeah, one more there.
Thanks. So you said you introduce the dispersive interaction between the two modes by slightly offsetting the junction to create this symmetry. So in a more complex circuit where the capacitance matrix will be more complex, how well can you predict the dispersive interaction?
Well, numerically, it's possible to do it without much problems, since so for more distributed circuits with more modes and so on, its question is how well you can solve Schrödinger equation for that, and that's only it. So far, this circuit is quite simple, only two modes there. So yeah, but in the end, it's up to, it becomes, the question is how well you can solve the Schrödinger equation with multiple modes. Maybe I'm not fully understood the question now.
We can talk later.
Oh, yeah.
Okay, one last quick question over there.
So you have only considered the first two modes, but there could be higher modes of the geometry as well. And do you have to worry about coupling of your qubits to those higher harmonics? And how do they affect, for example, the qubit coherence?
Yes, that's a good question. That in principle, we have quite a lot of modes in this CPW, and they're going to affect. But these modes have quite high frequencies, so their effect can be incorporated by proper normalization of capacitance and inductance of the lumped element capacitance and inductance of the circuit I have. Of course, if we go to high frequencies, or even in principle operating at the zero flux quantum sweet spot where the Unimond frequency is much higher, then this approximation becomes less accurate.
Okay, let's thank the speaker. So now the last talk of this session by Axel Eriksson from Chalmers University, who's going to tell us about universal control of bosonic mode in a planar superconducting nonlinear resonator via native interactions. You have 20 minutes.
Okay, thank you very much. So we just put this on our archive this morning, so we have a slightly shorter title now. So it's what I will talk about is universal control of bosonic modes, and we will do this by drive-activated intrinsic cubic nonlinearities. So this work was performed at Chalmers, and we're part of the VACT Center, which aims on building a qubit-based quantum computer. But I'm more interested in these linear bosonic modes that we already heard quite a lot about. So generally, when we want to do quantum information processing, we can, of course, use qubits, but then we need quite many of them because we need a large Hilbert space and to be able to control the quantum superposition of this large Hilbert space. And also, if you want to do error correction, you need even more qubits so that you have a redundancy of quantum states so that you can encode and protect the quantum information. And this is, as we already heard, some motivation for why to be interested in linear modes, because they have access to a large number of quantum states. So in principle, we could encode information in here redundantly. But there's also like an issue with these linear modes, and that's that they are linear, which means that we are not able to universally control the quantum superposition inside a bare linear mode. As we already heard as well, we need some kind of nonlinearity to manipulate the quantum states. And this is typically done by putting it in dispersive interaction with an ancilla qubit. So for example, as we have here, we have the 3D cavity, that is the linear mode, and we inject or insert this qubit chip that provides the nonlinearity so that we can have universal control of the bosonic mode. So if we would drive the cavity and the qubit potentially at the same time, for example, the Yale group pioneered in showing that they can have universal control over the state inside the cavity. So here they prepare a very nice Fock state by this approach. And in principle, they have universal control here, so they can prepare any kind of state that they want. So this is a very capable platform, but it also has limitations, and some of the most severe limitations come from the qubit itself. And some reason is because the qubit is typically much shorter lived than the cavity mode itself, which means that if you activate the qubit, it will relax during gates and limit the performance. And also it will induce kernel nonlinearity into the linear mode, basically coming from the dispersive interaction and the hybridization between the two different modes. So if we prepare a quantum state inside the cavity, this kernel linearity will over time smear out or scramble up the quantum information inside the cavity, which of course is an unwanted effect. And also typically this dispersive interaction is quite weak interaction, which leads to slow gates, typically on the microsecond timescale. So what I will present to you here today is a new idea for how to create a bosonic architecture without the ancilla qubit as a control unit. So the thing that we would like to have here are fast interactions, not limited by any dispersive interaction with a qubit, for example. And we also want to suppress these unwanted, always on static kernel linearities. But then, of course, we know that, okay, we have a linear mode, so we need some kind of nonlinearity to be able to achieve universal control. So the main idea here in this work is to have drive-activated nonlinearities. So that basically means that what we really would like to have is a system that if we don't drive it, it behaves as this black circuit, just a linear LC circuit. But when we drive the system, we can still induce nonlinear interactions by basically closing this nonlinear switch here. So that's the basic idea. But then we also need to have some kind of nonlinear element that can fulfill these requirements. And a very good candidate is the so-called snail element. So it basically consists of one small junction in a loop with typically 3 other larger junctions. And we can write down the potential like this. There's one cosine for each of the arms. And what's interesting with this one is that we have this control knob, the external flux through the loop. And if we would Taylor expand these 2 cosines, we can tune the flux so that we can cancel the expansion at one of the orders. And for example, we can cancel the 4th order term, which is the current interaction that typically hits us. So we can tune it to the curve-free point and have a strong 3rd order interaction, but cancel out the 4th order interaction. And this has been used in many contexts, for example, in amplifiers or couplers between bosonic modes. But what we will do is actually to take this element and put it inside the linear mode itself. So we have a linear resonator here. We put a snail at the current antinode, which brings this nonlinear potential into the linear mode itself. So to begin with, it just looks completely messy, because when we expand the Hamiltonian, it will just contain terms on all the different orders. But let's try to look into what these different orders actually will contribute with. So if we start with the first term, all of these will have flux dependency, and they will depend on, they will have one DC component and one AC component that we can drive. So if we don't drive the system at all, there would still be a DC component here. But if we just do proper normalization, proper diagonalization of the system, this constant force will just be incorporated in the or in the mode itself. So this term doesn't really show up, and the same is true for the quadratic term. If we don't drive it, proper diagonalization will just take care of this part. For the 3rd term, it will have this DC part, but we can also see that if we expand the cube, we will have a not equal amount of A's and A daggers, which means that these are off-resonant interactions, and at least to first order, it will not really give any contribution. And again, if we don't drive it, it will also not show up in the dynamics. The 4th order is problematic, because if we expand it, we will have an equal amount of A's and A daggers, and this will result in the Kerr effect that typically scrambles our cavity state. But here we had the opportunity to use the static flux and tune this coefficient to 0. So we do that, and we don't drive it, so we can also cancel this one. Then there will, of course, be higher order corrections, but these are typically small. And we also have a charge pump, but let's not drive the charge, so we also don't have that term. So very nicely, we're back more or less in a linear oscillator, if we tune it in this way. So let's look on what kind of interactions we can now have in this system. So just the trivial dynamics itself is what we can call the Fourier transform interaction. And if we now start to drive the system with a 1 omega flux tone, we can capture resonantly the 1st order interaction, and this is just resulting in a displacement. So for a bosonic mode, it's easy to imagine this in the Wigner space. A displacement is just a translation of the state that we have in the state, or in the cavity. And if we drive with twice the resonance frequency, we can engage the quadratic term, which will result in squeezing. And these are a so-called Gaussian interaction set for our bosonic or continuous variables mode that can transform a Gaussian state into another Gaussian state. But that is not enough, because we need some kind of nonlinearity to have universal control to prepare any kind of quantum state that we want. But we can achieve that as well if we drive with 3 times omega, because then we can capture this cubic term, or part of the cubic term, with an interaction called tri-squeezing, like a generalized squeezing. And that promotes our interaction set to a universal set. So in principle, by combining these different interactions, we have universal control and could in principle prepare any kind of state. So this is really the goal, try to demonstrate that we can do this. So let's run to the lab, and we produce a chip. So we have a cavity here. We put a snail at the end. We also do have a qubit here, but this will not be participating in the control of the cavity state. It's just there so that we can do Wigner tomography of the state, so we can really show that what we do with the snail cavity is really what we claim. So let's characterize the state or the system. We look on how the frequency of the mode changes as a function of flux. And we can also look on the coherence of the system. And what we can do is that we fit this nonlinear tuning curve and extract the coefficients or the parameters of the system so that we can predict what are the strengths of the nonlinearities. So we do that. And we see here that the effective Kerr nonlinearity, the effective fourth order nonlinearity, is this orange curve. And we are measuring the effective Kerr as well with these blue dots. And the dashed line is the third order interaction. And we can see here that at this point we are crossing zero. So we're canceling the fourth order interaction, but we still have a strong third order interaction. So this is really the work point where we want to be, where we have more or less a linear oscillator if we don't drive it, and then there might be this possibility to use this third order interaction to drive it. So let's start to drive it. We drive it with 1 omega, not so interesting, it's just a displacement. We drive it with 2 omega, which will start to squeeze the state. And this is also quite fast squeezing compared to the dispersive interaction with the qubit, which typically takes a microsecond to do any gate. Here we do it in 20 nanoseconds and squeeze it quite strongly. And we drive it with 3 times the omega, and we do this generalized tri-squeezing that produces this non-Gaussian state, and we can even see that this is a Wigner negative state that we have in theory and experiments here as well. So for continuous variable systems, this would be considered a resourceful state. And another resourceful state that is more extensively considered is something called a cubic phase state. And that could be produced by first engaging squeezing and then engaging a cubic interaction. And we should note that it's slightly different than the tri-squeezing here. But the squeezing interaction is just the same as we already had, so that's prepared for already. In principle, since these interactions is a universal set, we could decompose this cubic gate in a series of these other gates. But what I will show you next is that we also can synthesize the cubic interaction natively within our system by preparing pulses in a different way. And again, here the problem that we have in principle here is that the cubic interaction not only contains this cubic power 3 terms that we have in the tri-squeezing, but it also includes these cross terms. And I already showed that we can engage the power 3 terms by the 3 times omega flux drive. But we also see that we can resonantly capture these terms if we would just drive with a 1 omega flux tone. But the issue with that is that it will also engage the linear displacement drive itself, which will just be much stronger also because it's a lower order interaction, whereas this is third order. So this is actually much stronger. So we'll just, if we apply this, we'll just displace the state away, which is unwanted. But we also have the charge drive that only couples to the linear displacement. So if we prepare a pulse sequence like this, we drive with a 3 omega and 1 omega flux, and then we have a charge drive in the opposite direction, we can cancel out the effect of the linear drive and only capture the full cubic interaction. So this will really be a cubic gate. And if we first do the squeezing gate and then the cubic gate, we can prepare a cubic phase state that looks like this. And this is also, again, fast interactions compared to the dispersion regime. And also it's a quite high quality state, and one way to quantify this is to look on the section here and see what is how pronounced these negative ripples are. So to conclude, what we have worked on with here is a bosonic mode with drive-activated nonlinearities. So again, the very basic idea would be to have an oscillator that is linear if we don't drive it, and if we drive it, we can engage different nonlinear interactions. And we also showed a quite easy universal interaction set by just applying a single monochromatic tone, either at 1, 2, or 3 times the frequency, And we also showed in the last part here that we can also synthesize other types of gates natively, and we can also combine different gates to, for example, produce a cubic phase state. So thank you very much.
Okay, we have some time for questions. It's over there.
Thank you. Could you comment on the possibility or capability for quad squeezing?
Sorry, for?
For quad squeezing drive, fourth term. Fourth term of the driving, A to the 4 plus A to the 4.
Sorry, you mean if we would drive the fourth order term? Yeah,
yes.
We haven't done it, but in principle we could do that as well. So that would be, in a sense, it would be a generalized fourth order squeezing interaction that in principle we could do, but we haven't done it experimentally. But that could also be interesting to do, absolutely.
Okay, thank you.
Great talk, thanks. So I was curious, you still need a transmon for tomography?
Yeah, exactly. So for tomography, we still use the transmon, yeah.
Which means you still have a core element coupled to your resonator, and you also have dephasing from the cross-core to the transmon, right?
Yeah, exactly. So in our system here, we do have a transmon there for the purpose of doing the tomography, but we could also imagine that, okay, we actually don't need it for the bosonic control itself, so we could remove it and put this unit in a larger chip where we indirectly calibrate it with via other interactions. So the qubit is here only to show that what we claim that we can produce in the cavities mode, we really can produce. But we don't need it for the control. It's just there is a spectator qubit.
Okay, thank you.
I had a question. With the snail coupler, if you want to work in the curve-free point, it's also the point where you're very flux sensitive. Are you looking into other types of different couplers to be both curve-free and also at a sweet spot?
Yeah, that's a very good question. So the question here is, okay, we are at the curve-free point, and if we go back in the beginning, we can also see that we are quite flux sensitive, as you see here. And that is also the main limitation that we have currently, because basically we need to sit on this kind of point here. So that's one of the main limitations. And here we also do believe that, as you say, if we would be able to move the curve-free points closer to the sweet spot, for example, we would be less sensitive to the flux noise. So that is something that we are trying to look into, and we could also try to imagine a more complex snail architecture and maybe try to find a better spot of where we still can have strong third-order interaction, for example, or maybe fourth-order even, for the dynamic part, but really suppress the static fourth-order. Yeah, but it's one of the main limitations. Yeah.
So you have 3 different frequency drives for your to mediate the different interactions. Do you find that there are different limits in how hard you can drive for each of the different frequencies?
Yeah, if we look into, I can show you the archive version that's out now, and there we show that if we drive harder and harder, there will be a saturation of how much we can squeeze, or how much we can try squeeze as well. Some of these limitations also come from that if we produce a very, very highly squeezed state, the higher order corrections will be more detrimental. So we will start to squeeze, shear the state when they are very, very highly squeezed. So we also see that the fidelity of the squeezing and tri-squeezing goes down if we produce very, very squeezed states, which also in a sense then limits how much we can squeeze.
Okay, so with that, we come to the end of this session. Please wait for some announcements on the poster session, but let's thank Axel and all the speakers in this session first.
Awesome. So we nearly reached lunchtime, but some organizational announcement for what is coming up next. First, if you have a poster today, then please bring it up now. The poster session is upstairs, the next floor. So if your poster session is today, please find a free stand and put your poster up there. That's the first thing. Then, during the 3 hours that we have no schedule here, we have 3 workshops coming up from those awesome companies that support this event. And the one is happening in the room downstairs, which is called the Saturn, so the room on the ground floor in the corner, in that corner here. There we find the workshop from Quantum Machines at 1 o'clock and the workshop from Keysight at 2:30. And then there is another workshop by Crows, and this workshop takes place above us, essentially, 1 floor above us. So you need to take the elevator to 3rd floor to find that workshop room. But we have those guys with the white shirts, and they can help you find this way. It's pretty easy to find, so I guess you'll do it. Because I figured I got no questions about the restrooms today, so we were all able to find those. I'm pretty confident we were all able to find the workshop room Mars. So now it's lunchtime. We have 2 spots there. Ground floor and the poster session floor also has a food station. Enjoy lunch, have great conversations, and thank you for joining this morning.
Okay. Okay. Hi, everyone. I'm Angela Koo, if you didn't come to the morning session. So I'm an assistant professor at the University of Illinois at Urbana-Champaign, and we're going to have a session today on fabrication and materials. And it's my pleasure to introduce our first speaker, Donna Yost from MIT Lincoln Lab. So Donna is a specialist in integrating devices and has worked many years on integrating different types of devices. So I'm really excited to hear what she's going to discuss today on integrating superconducting circuits. So please take it away.
Yes, it works. I'd like to thank the organizing committee for this great conference and also for inviting me to talk to you about 3D integration technologies for extensible quantum processors. Superconducting qubit performance has improved by orders of magnitude over the last 2 decades and is now being offered in commercial products, which is very exciting. But even as these materials, designs, and fabrication methods continue to improve, we must also work to address the interconnect challenge. Here you see a device with with 1 by 5 qubits and the associated control lines and the readout resonators. And these components are critical to the operation of our superconducting qubits. For a 1 by 5 array, this works perfectly fine. But as you go to larger 2D arrays, such as even this 4 by 4 array seen on the right, you can see that it's very challenging to reach the interior of the devices and make contact to them. This can be accomplished with high-density routing and air bridges and wire bonds for small-scale arrays. But as the arrays get larger, it's going to become untenable to reach in and connect and communicate with those qubits in the interior. So we really need to move beyond the planar chip design into the 3rd dimension. Early classical computers faced similar challenges. Here you see 2 of the first integrated circuits. A circuit with 3 germanium transistors that are wire bonded together in a system in a package. And you see a monolithic silicon IC where it had 6 transistors. It was a flip-flop with planar wiring. Fast forward 30 years to the Pentium chips that had over 5 million transistors in just over 1 square centimeter. How did they do that? How were they able to communicate with all those transistors and get them to work together? And the answer is multi-level wiring. If you take a cross-section of another widely used integrated circuit, this TSMC Xilinx Vertex 7, you can see here the multiple layers of metallization that are separated by dielectric. And as the systems got more complex and more capable, we developed technologies such as microbumps for connecting 2 chips together and through silicon vias for routing signals through the silicon chip. This Xilinx Vertex 7 has actually 6 billion transistors with 2 million logic cells. And if you're doing the math, that's 3 million transistors per logic cell, just FYI. This is actually part of a much larger chip, where there are 4 FPGA chips, which are bump bonded to an interposer, which in turn is bump bonded to a package substrate. So these integration technologies, which were well developed for classical systems, they can be leveraged for us for our superconducting quantum systems. But there are special constraints that you need to be aware of when you're working with our superconducting qubits. One is that the dielectric layers in these multi-level stacks can really cause the qubits to degrade. Another is that many of these back-end line, these metallization technologies, have normal metals, which can also act as loss channels for the qubits and cause heating in your cryogenic systems. These technologies are being optimized, however, for use in the superconducting quantum qubit arrays by many organizations and companies. One is D-Wave, that has this advantage chip with over 5,000 qubits. And they accomplish this in a monolithic way, where they put the qubits right on top of and intermixed with the niobium superconducting wiring. And this allows them to have great connectivity in the system. But one of the trade-offs is the coherence times of those qubits. A lot of people, such as Google with their 72-qubit Sycamore that we heard about this morning, and Rigetti with their 80-qubit Aspen, as well as IQM with many of the chips that they have available, are using flip-chip bump-bond integration, which takes you into that second dimension, pulls your wires a little bit away from where your qubit chips are, and allows you to have really high coherence times. Along the way, technologies such as bump technology, as well as through-silicon vias, which we heard about last year from Chalmers and VTT, are being developed for superconducting systems, and many people are using these to connect the ground planes and reduce the chip modes as the chips get larger. At Lincoln Laboratory, we developed a 3-tier stack technology that allows you to have contact to that multi-level wiring, or connections with that multi-level wiring, without direct contact. So we separate the qubit chip with an interposer chip in the middle. And this interposer chip has superconducting through-silicon vias that allow the qubit chip to communicate with the multi-tier stack, but provides isolation. And we'll be hearing more about that later. IBM also uses multi-tier stack technology in their 127-qubit Eagle array. Today I'm going to talk to you about 3 technologies for integration, including planar, flip chip, and multi-tier stacks. I'm going to talk to you about what they can enable, or why we do them, what advantages they can give us for our system. I'm going to talk to you about how we make them, some of the trade-offs involved in that, some of the characterization and vetting that we have to do in order to use them in superconducting qubit systems. And I'm going to start with talking about planar devices. One tool that's really great to helping with the routing and the signal routing and signal crossing for planar devices is airbridge crossovers. So you can see here that this signal line is crossing over this transmission line, and this really is enabling for small-scale arrays, on the order of 4x4, maybe even up to 10x10 array, qubit devices, depending upon the density of your routing. It can also enable some ground plane ties and strong inductive coupling. The way we make airbridge crossovers is first we pattern the base metal, then we pattern photoresist to open up tether windows that act as the footing, the connection for the tethers for our air bridges. Then we ion mill, deposit aluminum, pattern that into the bridges, and etch it and strip it to reveal and make these little air bridges. There are a couple different challenges with this process. One is that your photoresist has to act as a mold for your air bridge, so you need to have really nice sidewalls on that photoresist. We also need to be able to ion mill the surface to get good contact between the air bridge and the base metal, so the resist needs to be able to protect the qubits which are under it and stand up well to this resist, so sometimes we need to use resist hardening techniques. And finally, we need to have a good clean etch. We do this process on both 50mm wafers as well as on 200mm wafers, and we use different wet and dry plasma etches and strips. After the air bridges are fabricated, we characterize them with chains of 24, sometimes more air bridges, and we measure the resistance of these chains across entire 200mm wafers with automated wafer probe technology. And looking at a wafer map really helps you see, where's your process falling up? What is it doing? So the resistance of this is great. This is all within spec, but you can see here that it's even a slightly bit higher at the perimeter. And looking into that, that's due to the fact that the etches the bridge a little bit narrower at the edge. So really having wafer maps and having a lot of data at room temperature for your devices helps you look at your process and tune it and optimize it properly. These airbridge crossovers are enabling for small-scale arrays. We can use them to connect the ground plane. And here in this design, we reduced the flux crosstalk from 40% down to 3%. We can also carry signals in them. So depending on the size of the tether, you can carry a certain amount of critical current. For this circuit here, we could carry 15 milliamps, which is really sufficient for qubit bias and control. And also, air bridges allow you to intertwine inductive coupling loops. So you can have a smaller loop running potentially a less of a current and get still strong tunable coupling. So these airbridge crossovers really enable new and improved circuit primitives and qubit designs. Next, I'm going to talk about flip chip bump bonding. With flip chip packaging, the qubit is flipped onto the interposer and bump bonded to an interposer tier. This really takes you into the vertical dimension and gives you an additional layer for routing the transmission lines, the control, and the readout. At Lincoln, we accomplish our bump bonding with indium bump bonds to provide both the mechanical and the electrical connections. Here you see a confocal image of some of our indium bump bonds, about 8 microns high, 15 microns diameter, and we use an underbump metallization of titanium for adhesion, platinum is a barrier, and gold because it's a noble metal and doesn't oxidize. We make large chains of these to characterize them with thousands of indium bump bonds, and we measure these daisy chains in a series configuration. So here you see the current goes through the bottom metal, up through the bump, and along through the top metal. So these are all connections in series. Any single point of failure will cause a high resistance or an open in your chain, and we measure these with thousands of connections, and we characterize the resistance. It's really hard to measure that small resistance, but we get an upper bound of about 240 nano-ohms per bump, and also some contributions from our underbump metallization. So these bump bonds provide highly reliable galvanic chip-to-chip coupling. One of the challenges about flip chip bump bond integration is to control that gap. So that gap will have an impact on your capacitance and your frequency of your resonators and your qubits. Here you see a graph of resonator frequencies. So we measured 6 resonators across this qubit chip. And you can see here that without anything on top of it, they're all equally spaced. When we put a silicon chip on the top of it, they shift as you would expect, but the goal would be to have them all shift evenly. In this case, they shifted unevenly, and that's due to the tilt, the difference in the gap between one side of the silicon chip and the other side. And that can cause unequal spacing of your resonators, which makes it really hard to design for. So you really want that to be even. Our goal is to have less than 100 microradians of tilt. And we accomplish this with etching silicon spacers into the surface of our wafer. Here you see a tilted SEM of our spacer with a post and the indium bump bonds. We measure the height of our post so that we can control that gap because that silicon will act as a hard stop. And here you see a cross-section SEM of a chip on top of an interposer, and the posts stop it, and the indium bumps compress, and this is controlled well to a 2-micron gap. We've since actually gone to a 3-micron gap because we have integrated air bridges in our flip chip. And our air bridges are about 1.8 microns tall, so we increased that gap going to 3 microns. The results that we are getting with flip chip integration, some of our early results were with flux qubits that typically had about 14 microseconds in the planar configuration. And when we flip chip bump onto them, here you see an infrared image looking down through the top of the silicon chip. You can see the qubit loop, and the bias line is in the bottom loop. We got around 15 microseconds on this early demonstration, which was great at that time in 2017 and really validated that this process was viable. Since then, our flip chip qubits have improved in performance, and we're investigating putting the posts right next to the flip chip results, and we can get T1 times of about 45 microseconds. And now we have transmon qubits that we are bump bonding in this flip chip configuration. So here you see an infrared image of a flip chip transmon, and the performance of this transmon is about 47 microseconds. This transmon has both the post-processing as well as the flip chip integration. So we hope to look at moving the flip chip processing, the spacer post-processing onto the interposer, and we really hope to get closer to 100 microseconds with this T1. But a lot of people are using this flip chip configuration, and there's a lot of room for optimization of these technologies. And as the qubits get better, you really need to look at the integration technology and their impact on the qubits, because it's kind of like leapfrog. The qubits will get better, then the integration technologies have to evolve to go with them. And there's a lot of space right now for optimizing these technologies. And there's a lot of opportunities for optimizing these architectures in the flip chip configuration. Chalmers had a recent publication where they show flip chip transmons with over 90 microsecond time average T1 times and 99.9% single qubit readout fidelity and 98.62 qubit fidelity. And this is in a flip chip configuration with an 8 micron gap. Righetti's showing multi-chips with entangled gates, all bonded to a single interposer. Last year, you heard from Mario Palma about 20 micron tall electroplated bumps. So there's a lot of opportunities here for working with flip chip bump bonding, for optimizing the architecture, for having flexible designs and technologies to move this technology forward. One additional benefit of going into the flip chip is that with careful design, you can significantly reduce your crosstalk. So here you see crosstalk matrix for a 3x3 array in a planar configuration with 9 qubits, and that was about 10%. When we optimized the design and measured a 4x4 flip chip array, the crosstalk was actually less than 1%. And I invite you to read this recent paper by Cora Barrett, which discusses the calibration and the measurement of this array. So we've seen how integration methods, including air bridges and flip chip, can really help you realize small-scale arrays. But in the final section of my talk, I'm going to discuss how multi-tier stacks can help support integration for even larger arrays, allowing for even greater system complexity and capability. I'm going to jump back to some of the pictures that we looked at before. And I have to say, I don't know exactly what future complex processors will look like. I think they'll probably have many different forms depending on the application and the system needs. But I'd like to imagine that we can have the quantum processors which should have all the flexibility of integration as were afforded for these Xilinx and other advanced computer chips. We have multi-level wiring technologies. At Lincoln, we have a state-of-the-art niobium process, which is up to 10 metal layers. This is a similar process to what we use for fabricating our TUPA chips. And these are all planarized for great yield and consistency. This can allow for low crosstalk, high-density routing. You can carry RF signals in here with shielding on the above it and below it for great fidelity of your signals. But again, these stacks have the lossy dielectrics that can really impact the qubit performance. So how can we have our cake and eat it too? We can go to this 3-tier stack technology. So the 3-tier stack technology allows you to have this connectivity by access to this multi-level routing while preserving your qubit coherence. You have these large silicon, high-resistivity silicon wafers to preserve your qubit coherence, where your fields can be contained in that high-res silicon instead of losing its energy to the dielectrics in your multi-level wiring. This also allows you to have independent layer optimization. So as the qubits improve, you can swap those in. As you get different routing methods, you can swap those in. So this allows for you for great flexibility and optimization of all the different technologies. One trade-off of this is that it is more complex. So there is increased complexity. You have to have well-vetted design rules. You have to have people experienced to design into them, and you have to pay attention to all of the different complexities. But a bonus is that you can have additional functional layers and components on the interposer that can help you further miniaturize and get higher density circuits. So I'm going to talk to you next about the fabrication process for making this interposer and the high aspect ratio TSVs. So in our interposer process, we choose to do via etch first. You can do via first, you can do it last, you can do it in the middle. But for us, we chose to do it first because that gives us the greatest flexibility in depositing our superconducting liner. So we deposit that liner and pattern it, and then we do underbump metallization for eventual hybridization into the 3-tier stack. Then we take that wafer, we flip it over, we bond it to a temporary carrier wafer, and we reveal the TSVs on the backside, so you can make contact to the other side of the via. We do additional metal processing and patterning on that backside, and we can even fabricate qubits on there. And then eventually it gets integrated into this 3-tier stack. We run this interposer process on 200 millimeter, that's 8-inch wafers, using a CMOS tool set. So we have great control and reproducibility of our process. We can run batches of wafers in cassettes on automated tools and use the process metrics, the in-process metrics that are associated with a back-end-of-line CMOS technology, which really helps us to have good yield and reproducibility and reliability on our process. I'm going to go into a few more details about the process. So one important area is this high aspect ratio superconducting through silicon vias that can really provide with small form factor signal routing. Our via is 10 microns by 20 microns and 210 microns deep. We etch it blind using a Bosch etch, which is alternating cycles of etching and deposition, so you can get a very, very straight sidewall. The seconds are like maybe 2 seconds for each of your steps, your deposition and your etching. So you can get very slight scalloping on your sidewalls. And that enables you to deposit superconducting material all the way down into the base of it. Now, one of the trade-offs, it is much harder with these high aspect ratio, with the very vertical vias, in order to get good material. There are a lot of people who make their vias a little bit more sloped, like Rigetti has some good sloped vias, and Delft has some beautiful hourglass vias that are a little bit easier to deposit the superconducting material in. And those form factors are great for using for connecting your ground planes, which work really well. But for us, we wanted these high aspect ratio TSVs so that we could really use them to engineer the electromagnetic modes of our connections. So here you see a tilted stem of an interposer chip, and the connection is right here in the middle, and there's additional TSVs around the outside of it, which engineer those electromagnetic modes so that you can really control the quality of your coupling for your control and readout circuitry. If we had even made this 500 microns or even 100 microns, it wouldn't allow us that flexibility in design that we have with these high aspect ratio TSVs. So that's why we made that choice to do that, to enable really good, high quality, dense circuitry. So after we etch and line the TSVs with titanium nitride, we pattern that titanium nitride, then we flip over the wafer and bond it to a temporary carrier wafer. It's really important to have a uniform bond line. This is an adhesive bond. Here you can see a scanning acoustic micrograph of this bonded wafer, and it's very uniform. The reflection depends upon the gap, so you can see the TSV patterns. So you're actually looking through the silicon wafer, and you can see where the TSV patterns are. Here you can see it's a repeating array, again, using the semiconductor process equipment. You get 12 copies on each wafer of your entire reticle, which may contain up to 64 different designs. And you can see here one of the we have a very long TSV chain in this design. But you can see that it's a very uniform glue line, and you can even see one defect here, so you know it's real data. But these adhesives do need to be compatible with all of our processes for the backside metallization and the qubit fabrication. So on both sides of the interposer, we can fabricate resonators and qubits. We can fabricate additional elements. And here you see a spiral resonator, which is on the front side of the wafer, and your TSVs here. And here you see that connection again to the bias line on your qubit. In process, we measure a lot of parameters. So we measure the critical dimensions, which can play to the frequency of your resonators. We measure the alignment accuracy that can really play into your design rules, how tightly you can pack your components. We monitor wafer bow. We like to keep our wafer bow less than 100 microns, because then it can go through all the automated tools. And also, when you release the wafers, it's easier to bump bond the flat chips into the stacks. And we measure metal sheet resistance, because that can have an impact on the critical current, as well as the kinetic inductance, particularly of our tinitride films. After the wafers come out, we measure a lot of parameters across the entire wafer using automated equipment, including contact resistance, snake comb isolation, continuity, as well as our Josephson junction conductance. I'm going to talk a little bit now about some of the tests specifically that we do on the TSVs. One of the parameters that we do measure across the entire wafer is the resistance of our via chains. So again, you see here there is a chain of metal where the current flows through the top side, down through the TSV, and then along the bottom side and back up. So these are in series, so any single point of failure will cause a high resistance or an open. And here you see 100% yield across this wafer with a very consistent resistance. We characterize these also at cryogenic temperatures. So we measure the critical transition temperature. Here you see the tinitride, the planar film, the tinitride that's down in the via, and even the aluminum transition. This has a critical temperature much greater than our operating temperatures of about 20 millikelvin. And we measure the critical current of these chains. So our goal is, of course, 100% yield. You can see here that a couple fell out. But for the majority of our via chains, and here each one of these different colored dots represents a different chain of a device that was measured, our goal is to be above 10 milliamps, because that really enables you to carry sufficient current to do flex biasing of many different devices. So we're very happy with our critical temperature and our critical currents of our TSV chains. It's also important to characterize the resonators that we can make on the surface. So we had fabricated and measured some flux qubits on the surface and got T1 times of 10 to 20 microseconds. Another one of our goals is to enable high-density qubit arrays. This means making even more compact devices. So several compact form factor devices have been designed, fabricated, and tested using this TSV interposer technology. The standard readout of a lot of these qubits are these coplanar waveguide resonators, which are very large. We can replace those with smaller spiral resonators. I'm not doing that. With smaller spiral resonators, they can have a much more compact form factor. And we've characterized TSVs, transmon TSVs that are bump bonded to these spiral resonators. And here you see some data from fixed frequency and flex tunable transmons. The fixed frequency have T1 times of about 30 to 50, and the tunable have T1s of about 10 to 40 microseconds. And this enables us to read out the devices with high fidelity, greater than a 5-to-1 signal-to-noise ratio in less than a microsecond. We've also replaced the capacitor with a TSV device, with a TSV that can have a high capacitance density. So here you see, to scale, a transmon qubit with the capacitor color-coded in red that can get replaced with a TSV capacitor, and a coplanar waveguide resonator, which can get replaced with the spiral resonator. And so this allows you to have a significant reduction in the size of your element. So this enables us to make some compact qubits, as well as read them out and control them with novel circuit elements. Going back to our fabrication process, we do release these interposers. We bump on them into 3-tier stacks, which include a qubit, the interposer, and the superconducting routing module. And we characterize those also using similar daisy chains, but this time the current goes through the interposer, up through goes across the multi-chip wiring, up through the interposer, across through the qubit, and back down. So each link in the chain has 2 bump-on connections and a TSV, and we still measure critical currents above our goal of 10 milliamps. For chains with lengths of 1,600, and we measure a lot of the taps, the various single rows of those chains that have about 77 links, and we measure the critical current carrying in those. So we get this critical current in thousands of links and multiple 3-tier stacks, all above 10 milliamps. And we've used this technology to make small-scale quantum arrays. So we made an annealing test device of 25 capacitively shunted flux qubits with independent X and Z control and a fast, high-fidelity readout. More recently, we've been leveraging this technology for gate model applications and quantum simulation. So we have exciting first light of demonstrating transmon qubits integrated in this 3-tier stack. So we have a qubit tier with 5 transmon qubits on it. We have an interposer tier that also has transmon qubits, as well as the readout resonators and transmission lines that connect and get read out through the multi-wiring chip. And here you see the T1 times of our qubits on our qubit tier are about 35 microseconds. The performance is a little less on the interposer tier, which is not surprising given the the additional processing that you see on that interposer tier, but we are really excited about this first light for these transmon qubits. So in summary, I hope I've convinced you that 3D integration is critical for the extensibility of our superconducting qubit processors. These technologies must be optimized for use with superconducting quantum systems. And these multi-tier stack platforms provide flexible options for connectivity and compact high-performance circuit elements. Superconducting qubit architectures and algorithms continue to evolve, and future quantum processors may take many different forms depending upon the applications and the system needs. But these integration platforms provide flexible, configurable options for developing the hardware necessary to meet the system needs for extensible quantum processors. So I'm looking forward to seeing what all you designers and experimentalists and theorists come up with, because we're up to the challenge. And I'd really like to thank our team at MIT Lincoln Laboratory and at MIT campus, led by Will Oliver. We have a lot of dedicated scientists and theorists and experimentalists and fabrication people. We have a wonderful microelectronics lab at MIT Lincoln Laboratory that fabricate the devices, including our superconducting electronics, as well as our interposer wafers and our qubit and other interposer tiers. And I'm happy to take any questions.
Okay, thank you for that really great talk. We have lots of time for questions.
Thanks, that was really interesting. How uniform are the junctions across a wafer that you can make that couple to the vias and so on?
The question was, how do we form the junctions?
No, how uniform are the junctions across a wafer? If you make an array of transmons, you've got junctions across the wafer. How uniform are the junctions?
So we use the same process that we use to make the junctions on our wafers that aren't TSVs. So we use a shadow evaporation process with Dolan Bridge and E-beam lithography.
I think his question was, what's the uniformity across the wafer for the junctions? Is that right?
What's the junction uniformity? So in general, our uniformity on 8-inch wafers is about 5%. We do a lot of our work on in junctions. We fabricate on prototype wafers, which are 50 millimeters, and then we fabricate the interposers as well as qubits on the 8-inch wafers, and those are run about 5%.
Thank you. That was a really excellent presentation. I have a question actually about the scalability in the manufacturing process. So I know like in traditional chip design, like in GPUs, there's a lot of really robust kind of pre-silicate testing software. How scalable is the manufacturing process here, especially for like the multi-tier stacks? Like what's, as kind of demand grows, what does that look like for you?
So that's actually one of the beauties of this technology. So we're using a high-mix, low-volume CMOS fabrication facility that can make tens of thousands of wafers. I mean, this is extremely scalable. This is standard CMOS semiconductor equipment. There's some special tools that you need for making the dosics of junctions and things like that. But a lot of this technology, particularly for the interposer and the superconductor, a lot of this technology is extremely scalable. So we can leverage decades of CMOS manufacturing technology to make these superconducting qubits, to make the interposer wafers, and to make the superconducting electronics. So it's extremely scalable.
Thanks for the very nice talk. I was wondering, you showed that in your in your multi-tier device, you had qubits that were on the interposer layer and on the qubit layer. And on the qubit layer, they had significantly higher T1 times. So I was wondering, did that qubit layer have TSVs fabricated into it? And
It did not. It did have posts,
Okay.
but it did not have TSVs. We have the TSVs generally on the interposer wafer, and we put qubits on them. That was our first time with transmon qubits. So we look forward to even using better designs. So since we made those, our transmon designs have improved significantly. They seem to be improving every month, really. And so what we'd like to do next is to put some of our best transmon designs on those surfaces and see the impact of that. As you get your technology better and better for your qubits, then you'll become more sensitive to different things. So we need to continue to iterate on that. But we were really pleased with those results for first light on our transmons.
So do you think that at the moment the TSV fabrication it impacts qubit coherence then?
It undoubtedly, it has to, right? Because you're doing grinding and CMP on the back of that surface, and there are technologies that you can probably do to mitigate some of those effects, but you need to have something sensitive to identify them. So we do make resonators, and we do make transmon qubits on those, and as our technology improves, we'll continue to iterate and go back and forth and work on those issues.
Thank you.
But right now, we're really pleased with, the performance that we're getting, yeah.
Thanks for the nice talk. It's always impressive to see what Lincoln Labs is up to. I have a question maybe more about the process that you use for the TSVs. So after all of the scalloping from the Bosch etching, do you do anything special to clean and get the sidewalls really straight?
We actually have a paper on the archive that will tell you this, so I'm not giving away any secrets. And we do a thermal oxidation, and then we strip it.
Mm.
Yeah, and that's one of the reasons that we choose to do a via first, right? So if you do a via last, you can't do that because you can't have the high temperature processing.
Mm. And what process is actually used for the titanium nitride? This is ALD, or you do some sputtering or something in between?
So we have investigated a lot of different technologies, and what I can tell you is that it's a CVD technology, and that is also in the archive paper by Malik and Yost.
Thanks.
Hi, yeah, great work. I was wondering for the indium bumps, do you activate them? Do you strip the indium oxide before flip chip bonding, or you just break the oxide when you bond them together?
We strip off the oxide before we bump bond, and we do our indium bumps directly to underbump metallization on the other side. So that's why we have the gold in there, right? So we have the ti-platinum gold underbump so that the gold's a noble metal and doesn't oxidize very much, but we strip off the indium oxide before we bump bond.
And can you comment on how you do it? Is it a plasma process or?
I think I can tell you, but let me double check, and please connect with me, and I'll let you know if we can.
Okay, sure.
Okay, thanks. I better double check.
Yep.
Okay, I actually have a question. So you showed that the crosstalk is much more minimized when you do the flip chip technology. Sorry, the crosstalk is much minimized when you use the flip chip technology. Do you know what still remains that causes the extra crosstalk once you do the flip chip technology? So even though it's much decreased, you still have a little bit left over, and where does that come from?
Right. My understanding, and I'm a fabrication person, so my understanding is that flex crosstalk can arise from the application of the bias and also from the traveling back of the signals back into the ground. So I think there's a lot of optimization that can be done on the design to keep the signals far away from each other. And also, I think you want to make sure that your return path is very clear and also doesn't cross any of your signal paths or get in the way of any of your other qubits. And I would think as far away as you can get it from the other paths would be better. But I believe there's a lot of optimization going on in that design space, and it's kind of tricky to measure and calibrate, I get the impression. And so I think that the machine learning methods that are in Cora Barrett's paper, I think will really help with that, because maybe we can characterize a lot of different designs.
Okay, are there any other questions? Okay, then let's thank Donna for the presentation. Okay, so next we have Wei Liu, who will talk about development of quantum processing units at IQM.
Okay, all right. Good afternoon, everyone. I'm delighted to be here to
share some exciting insights into the development progress of our quantum processing units where we fabricated at IQM. So let's dive into the intricate details of our QPU processes. So in this presentation today, I will introduce our IQM Foundry first, then the core component of the superconducting qubits, which is including the characteristics and the performance of superconducting base layer, fabrication details and the measurements of the Josephson junctions, characteristics and distribution analysis of the indium bombs, and ensuring the precision during assembly for the flip-chip bonding. So finally, I will show you our 20-qubit QPU's impressive uniformity and the yield. Right, our IQM Foundry is located in Espoo, Finland. So it stands as a physical manifestation of our vision. With an investment of 20 million euros, we've not only created a facility here, but also a center of excellence that radiates with cutting edge. Spanning an area of 560 meters square, our foundry isn't just a workplace. It's also a playground for the quantum experts alike. At IQM Foundry, we have fostered an environment where the industry-level quality can meet the innovation. Our facilities encompass almost every step of the quantum precise units. So from the conceptualization to the realization, with a dedicated space for the fabrication, new material research, and 3D integration and for product delivery, we have crafted an ecosystem that accelerates our quantum ambitions. Okay, let's begin with the foundational superconducting base layer. The choice of the niobium as our superconducting material is driven by its robust properties and wide adoption in the field. We utilized a 4-point probe DC measurements to measure the resistivity across a very wide range of temperature from 300 K down to 10 milli-K. By leveraging this data, we pinpoint the critical temperature, a fundamental parameter that indicates the transition from the normal to superconducting behavior. So we achieved the TC is around 9.16 K. We also did some AFM analysis. The surface roughness is around 1.75 nanometer. And to be mentioned about this, one key metric in the material categorization is very important is the residue resistivity, which we characterized as only 1.18 milliohm centimeter. And another very important metric characterization is the residue resistivity ratio. And this triple R gives us up to the 14.3. Of course, we also have done a lot of other materials studies. And in here, I only focus on the niobium. And if you want to know more details, please also follow my colleague Wei Liu's poster. Right, for a deeper understanding, we also fabricated a chip with 18 resonators to benchmark the coupling factor and internal quality factor, which spans from the 4.5 gigahertz to 6.5 gigahertz. The internal quality factor, on the other hand, offers the insights into the energy losses within the resonator itself. So we extracted at a single photon level, the QI stands at around 1.14 million at a single photon level. So this indicates our quality of our superconducting base layer. We also have fabricated some resonators on the other materials that has a very high QI. But in this talk, what I'm going to show you in the next are all based on the niobium. Okay, moving to the Josephson junctions. As we know, these junctions is the heart of superconducting qubit that underpin also the qubit functionality. We start to measure the BCS gap of the aluminum junctions. with the 4 probe measurements in the voltage bias. So the 4-point measurements is very important because the dynamic resistance of the sample varies quite a lot as a function of the bias voltage. So the tunneling resistance of the junctions was of the order of 15 kilo ohm, which yields the critical current is order of the 20 nanoampere according to the AB relation. And for all the junctions we measured, the BCX gap gave us around 200 micro eV. So if you see clearly on this IV curve plot and zoom in to the center area, we have very sharp features. And these sharp features are both on the sub-gap regime and on the gap edge. So which indicates we have the very low noise of the junctions. We're also able to measure the reliability of the BCF gaps. For more information, please also follow my colleague Sungu's poster. In addition, to make sure that our junctions is stabilities and robust state, we also perform some breakdown voltage measurements. As you can see, we designed a sample which contains a very large range of the junction size from the almost 50 nanometer up to the 400 nanometer. And the resistance at room temperature can cover from 1 kilo ohm to up to 30 kilo ohms. And we benchmarked over 20,000 junctions. And all these junctions shows the breakdown voltage around approximately 1.4 volt. And here is the squid, what we have fabricated across a whole 8-inch wafer. And we have fabricated over 40,000 squids on this 8-inch wafer. And it also shows our ability to scale up the quantum technologies. And each squid contains 2 identical junctions, which is 200 nanometer by 200 nanometer. And we achieved the yield around 99.75%. So from the right side, this distribution plot, you can see it also follows the normal distribution. And H square of the heat map of the room temperature resistance here contains more than 350 squids. And these squids boast a uniformity less than 5%. Right, next in line with the fabrication is the Indian bomb fabrication across the whole wafer. We have managed to achieve a yield 99.85%. So our focus spans across the various attributes, including the height, circularity, and area. We mainly focus on the center area and the edge area. The measurement of the height using an optical profilometer, and the quantification of the surface area and the circularity are extracted from the optical microscope images. So on the right side, you can see I show you some SEM images of our Indian bomb arrays, and the single bomb of this SEM image shows the bomb height is around 7.9 micrometer. Okay, this subsequent distribution plots offer a visual representation of the consistency that we achieved. So to analyze this distribution further, we observe some difference between the height, circularities, and the areas. What we have in here, the center area, the height of the Indian bomb is around 300 nanometer higher than the edge. And for circularities, there are no big difference. But for the area, we also notice some difference. The center area is around 6 micrometer square larger than the edge. Okay, come down to the final flip chip bonding. This is very important because in the intricate process of the flip chip bonding, we address the challenge of maintaining a constant gap over the unified chips due to the inherent tilt. And here I show you 2 examples of our samples. So we measured 5 data points on each side, and then we extract the tilt angles that ensure a total tilt of under 3 millidegrees. And if you transfer to the macro red, it's less than 50. Okay, with all the above successful technologies, I would say let's discuss our 20-qubit QPUs, which is also fabricated across the whole 8-inch wafer. On the wafer, our squids consist of the junction of the 2 groups of the qubit frequencies. Also, we also include the tunable couplers. Then there are more than 4,300 squids. As you can see the heat map and the histogram, we can clearly see the 2 separated groups of the qubit frequencies. So now the question is, how do we cherry picking the QPU for cooldown, since we have so many good QPUs? And the answer is we apply some criteria. For example, matching the qubit frequencies with respect to the design target, ensuring the qubit is sufficiently away from their respective readout resonator for sufficient per-cell protection, ensuring the qubit frequencies do not have a significant spread, ensuring for QPU with square lattice topology, the 2 respective sublattice group has sufficiently close frequency band, and also the differences in the maximum and the minimum frequencies on the whole chip should be limited to a value. And by applying all these criteria, we calculated the throughput yield, RTY, for the accepted cooldown QPUs is higher to 91.86%, which means we have almost 80 QPUs ready for cooldown. And here I select 1 QPU we benchmarked at low temperature. It unveiled well-separated qubit drive frequencies as we expected, which is 1 qubit frequencies group located at 4.1 gigahertz, and another group located at 4.3 gigahertz. And on the right side, as you can see, we also benchmarked the T1 time. It's around 60 microseconds for almost each qubit. Of course, our commitment to stability is evident as we examine the T1 time distribution across the 820-qubit QPUs. So here I show you 820-qubit QPUs we fabricated from different wafers, different samples. And as you can see, it's a kind of a constant median T1 times is around 16 microseconds. And for here, if you want to know more information like fidelities and 2-qubit gate fidelities, please follow Yoast's talk tomorrow. Okay, in summary, in IQM Foundry, we have a well-established and stable industry quality of superconducting base layer, Josephson junctions, indium bomb, and flip chip bonding processes. And our foundry also produced the 20-qubit QPU with high yield and good quality on 8-inch wafer level. Also, at our foundry, we are committed to pushing the boundaries, unlocking new possibilities, and to scale up for the future need of logical qubits. Of course, our success would not have been possible without the dedication of our fabrication teams. I would special to thank Yugen, Alexandre, Sungu, and Wei Liu. Also, our clean room teams and design simulation teams and the cryogenic measurements teams, and all IQMers. Our fabrication techniques definitely enhanced the IQM Spark. If you are more interested in this quantum exploration, please check the demo at the booth tomorrow. Thank you very much.
Okay, thank you for that nice talk. Are there any questions for Wei? Actually, I have a couple of questions. So for the T1s, they seem to fluctuate in time. Do you observe correlations in the T1s between qubits on different parts of the chip or qubits that are close to each other on the chip?
Actually, our design is quite nice, so we didn't see too much crosstalk and between the two different qubits, and the T1 gets affected because of each adjacent qubit.
Okay, and then also on your kind of heat maps of whether your junctions or your squids are working, it kind of looks like the ones that don't work are localized in specific spots. Is it like there's some defect on the wafer and then the rest of it just looks fine, or is it more? So on these heat maps, for example, it looks like there's like, let's say a big chunk where the qubits don't work, but it's mostly working in a lot of the wafer. So is it, when it doesn't work, is it like there's just some defect on the chip or something like that?
Oh, yes. So as you can see some white dot here, it's sometimes it's because of the defects of the contact issues, which we're probing. It's kind of outlier, shows some very large resistance. Or there are some like shorting junctions during the probing. So that's why I show the yield here is almost 99.09%. It's not 100%.
Oh, okay. So there, one here, and then also one in the back.
Can I, Gianluca Limodio from Quantware. So I have a question. When you deposit the junction, how critical is the roughness of the substrate? And if it is critical, what is the reason behind this? Thank you.
So are you referring the roughness of the junctions?
No, the roughness of the substrate underneath.
So sorry, I still didn't understand. Can you?
So basically, when you deposit the junction, you deposit on a certain substrate, right? Like I don't know, can be silicon, can be anything. So this can have some kind of roughness. So is this parameter critical for your junction behavior?
I don't know exactly, but we normally don't do some passivations for the silicon wafer before we deposit the junctions.
Okay, thank you.
Mm-hmm.
Thank you for your talk. So I want to ask you about what kind of effort to be needed to fabricate the junction uniform in such a large wafer?
Yeah, it's good questions. So as you can see here, so this data I was mentioned here is not include any kind of post-fabrication tuning, like laser annealing or the pre-composition from the squid designs. And this is very first data across the whole wafer we got from the 8-inch wafer. And everywhere the squids are identical. I would say this is related a lot to your process development, and especially your oxidation layer conditions and the rate of when you choose your deposition rate of the aluminum.
I see, thank you.
It's a great talk. Can you say something about the T2 times of this device? And have you looked at the two-level system problems in your in these processes?
Two-level system, yes. Sometimes we saw some two-level system across 1 or 2 qubits, but we already tried to minimize it as the very low level. So we didn't see very clearly two-level system across our QPUs.
Do you have any statistics like the two-level system density? Because qubits are fixed frequency, I guess it's hard to characterize them in terms of a broader frequency domain.
I think this information you probably can get more from the Yost talk tomorrow.
Thank you.
Okay, let's thank Wei again.
Thank you.
So next we have Jared Cole, who will be discussing new ways of measuring defects in qubits.
Thank you very much. I'd like to thank the organisers for the opportunity to speak. I realised that the last time I spoke scientifically in gassing was 13 years ago, and we were at a meeting of the then new project on solid-state quantum information processing for the EU, and it was a much smaller room with much fewer people and much fewer industrial sponsors. It really has come along in leaps and bounds. It's a very exciting time. Having said that, I'm here to tell bad news. I'm here to talk about the problems we have, the problems we continue to have, and the problems we will have. So here is the story that we tell funding agencies, VCs, and every time the iron trappers are in the room, yeah? Superconducting is fantastic. But of course, we're all friends here, so I'm going to say the quiet bit out loud, but they are imperfect. Unfortunately, the font, that's very disappointing. Even the font is imperfect. Maybe that's good. For instance, a Josephson junction, typically aluminium oxide, this layer is amorphous. You can see here's a TEM image I stole from some earlier work from Finland and Sweden that you can see it's not flat. It varies a lot across the device. It varies from fabrication run to fabrication run. It even gets worse. Here's a picture from my colleague in Karlsruhe where he started thinking about all the different places where defects can be, where there can be bits of stuff that limit the performance of the device. It actually gets worse because in glasses, we know from the 70s that these two-level defects exist. And there's something called the standard tunneling model. And when I first started working on defects, I would give talks at big physics conferences, and glass people would always say, this problem has been solved, the standard tunneling model. And I increasingly got angry with this question. And then when we finally wrote an article about this, we had this beautiful figure. And these are just some of the possible sources of TLS defects. We don't know which ones these are. We see them all in circuits. We can now measure them with much, much higher precision. That was the whole point of this article, was to talk about the precision that we can understand these things. And yet we still don't know at a chemical level what they are. And therefore we can't do anything about them apart from just trying process by process, testing things over and over and over again. So that's a concerning thing. I would like to be able to just say, you know what, don't put that atom in the circuit. But it's not that simple. These are often collective defects, effective models. They can be quite complicated, different techniques, because processes, because the fundamental symmetry is just that there are two levels. And we all know from quantum mechanics they can come almost in any form. Why am I belaboring this whole point? Everyone in this room needs to think about this number. Yeah? This is the target. Now, I'll correct my usually I say this is the fidelity, but last night I learned that probably noise entropy is a better way of describing it, which is excellent. It appeals to the theorist in me. But we need all of the numbers to be as good as possible. Yeah? We need to be able to control as precisely as possible. We need the minimum amount of crosstalk we can possibly have. We need the best calibration we can have of the qubits and the resonators. We need them to be stable over time. We need them to have long lifetimes, long coherence times. That means we're going to have to look at every aspect of the chip continuously. You won't be able to just optimize one part and then you're done, and then go over here. In fact, Donna said really well that we optimize the qubits and then we optimize the integration. Then we optimize, and that is for every aspect. This is what the silicon people did. It cost billions of dollars. Let's hope it doesn't cost that much again. Yeah? But this is what we need to do. I'm a theorist and a computational person. I don't have a dilution fridge. Thank you. I don't have fabrication, anything like that. But I do speak experimentalists fairly fluently, and some of my best friends talk to chemists. So I really, I figure I kind of understand these experiments. What I'm concerned about is, when we improve all of these things, we also need to improve the theory and the computational modeling that goes with it. And in fact, there's also an arms race. As we learn more from the experiments, we have to develop the theory, and vice versa, because otherwise we can't understand what's going on. So today, I'm going to tell you 3 little stories about examples where we did crazy experiments which turned out to point out significant holes in the theory. Unfortunately, the first 2, I don't have the holes plugged yet for the theory, though I'm working on it. And the third one, we have, it turns out we were almost there ahead of time, but not quite, and I'll show you why. So the first story is just about stability. And it's just about how long do things hang around. So my friends in Sweden, in Göteborg, led by Johannes Bielander, did a crazy experiment. They set up a fridge, they set up the measurement, and they got 3 different types of resonators with approximately the same frequency. So the one on the far left is a superinductor nanowire resonator, the one in the middle is a coplanar resonator, and the one on the right is one of these beautiful 3D cavities. They put them one by one in exactly the same fridge, exactly the same electronics, filters, everything, exactly the same analysis. And in each case, they did a long time measurement of the drift of the resonance frequency. So that's what this curve is. And you can see it's wiggling around, and this is my new favorite unit as a theorist, kiloseconds. So these are long measurements. And you can see it drifting around, and you immediately see it looks a bit random telegraph signal-like. Yeah, it does some stuff, and then it jumps to something else. It actually looks very much like a multi-state random telegraph signal. And so what they then did was they did a whole bunch of interesting signals analysis on this. And so you can kind of see the nice rainbow plots in the middle are histograms of the frequency as a function of power. And so the first thing you see is as you crank up the power, they get narrower. Motional narrowing, just like in the textbooks. Beautiful. As you pump up the power, they narrow. But what you see at this end, at the low power, is completely different behavior in the 3 different resonators. Sometimes you resolve the RTS jumps, sometimes you don't, sometimes they just smear into some distribution. And you see this in the bottom panels, this is just fitting the full width half maximum as a function of power. So this is the kind of thing you do when you just publish in a paper, a journal paper, yeah? You just fit to something, you say, oh yeah, it's a power law, it's fine, blah, blah, blah. And if you've got your nice 3D cavities, it's a very pretty match and you might get it into nature. If you've got your crappy one over there, well, then you might get into science, I don't know. I'll just move on. Maybe I got them the wrong way around. What's really nice is, because we have such long data here, you can also look at the power spectral density and the Allen deviation and really start to fit them to an RTS model. And an RTS model here has an amplitude of the fluctuations and a switch-in time. And we extract those 2 parameters. And we extract those 2 parameters as a function of power for all 3 cavities. And so you see there are some commonalities. The switch-in time scales with power, exactly the same for all 3 cavities. So even though, particularly at low power, it looked like they were behaving completely differently, when you analyze it in this way, they actually look very similar. You then, over on the left, you've got the RTS amplitude, and you see it goes with some power law, and then it flattens out and stabilizes to something else. Now, if everything worked as the theory book said, I wouldn't be telling this story, but it doesn't. Interestingly, the power scaling laws don't follow what you would usually expect from the standard tunneling model. Usually in the standard tunneling model, we would assume that there are some Landau-Zener transitions close to degeneracy for these defects, and as you drive near them, you can drive up to the excited level, and that's what gives a power dependence. It didn't work, it didn't fit. What does fit is you have those types of corrections, but you also have off-resonant transitions, stochastic resonances. And it turns out there's a thing called stochastic resonance where you can drive with a stochastic field which has a harmonic component which happens to be resonant with the transition. So even when you're far from the, not super far, but far further away from the resonance, from the degeneracy point, you can still drive these transitions. The first hint of that actually came from something Will Oliver did almost 2 decades ago. We found in some supplementary material for one of your papers. But then we went through and had to go through all the details of it to work it out. So the really cool part about this experiment, we're doing the same experiment with different types of cavities. So we're telling the difference between what is a common TLS problem across all cavities versus one that is technology specific. So that's very exciting. But second of all, none of that power behavior is in the standard tunneling model. So we need to extend the standard tunneling model to understand this, because that off-resonance is an energy loss source. When you've got your coplanar waveguides or any other kind of cavity on the chip, it's losing energy to those off-resonant transitions. So this is something that we have to deal with. Now I'm going to jump to something which is more obtuse, but lots more fun, listening to circuits. This is acoustic waves on chips. This is another Chalmers experiment, this time by Gustav Andersson and Per Delsing and his group. And this is gallium arsenide putting an interdigitated transducer on top and Bragg mirrors. And it's a cavity, but it's an acoustic cavity. And we did TLS physics with this cavity. It behaves just like the standard tunneling model, as you would expect. We're able to probe a bunch of different modes, which means that you can actually get a lot of information within the bandwidth of the experiment. You can probe all of these modes simultaneously and gain a lot of information. And do the whole experiment as a function of temperature, because there's no superconductivity here. This is just gallium arsenide. It's just semiconductor physics. So there's no quasi-particle generation above gap. And we can just do temperature-dependent measurements. We also did spectral hole burning. Everything worked, textbook, all fine. But what I like about this is you can do over a wider range of temperatures, we can check things, and yet it's still TLS physics. The reason I put it up here as a reason that we have to think about new ideas is this most recent experiment. We did the same thing. We probed a whole 11 modes simultaneously, and we correlated the signal between the modes. So you get, again, nice rainbow pictures, and there's part B there on the left. It's nice, quiet, it's doing its TLS thing, that noise fits very well, everything's fine. And then every now and again, it goes absolutely crazy. Yeah? You see this huge deviation, and it's anti-correlated in places. So we can calculate the correlation function in these large excursions, and one mode gets pushed that way, and another mode gets pushed that way. That's not what the standard tunneling model says. You should get a drag on the modes either way, unless there was some weird coincidence that it happened to only be in one point in time, or one point in frequency space. Now, some of you who've seen this kind of stuff in the superconducting states go, but that could be high energy excitations. We all saw these cool experiments where they took a dilution fridge and put it in a mine, like under the ground, and saw the effect of cosmic rays. It behaves in a similar way. But this is all semiconducting. There's no superconducting, there's no quasi-particles above gap. So these effects will also happen in the substrate. Yeah? This is not specific to the metal on the top that we're going to make our chips out of. So we may not see these effects yet. We may see them in 2 years or 5 years or 6 years' time in the circuits. But again, these are correlated over large length scales, which means the error modes that are generated in these circuits are correlated over large distances. And that we have to be careful about how we include them. The final one, some of you may have seen this stuff before, but I this has been my passion for a long time, is we have lots of tools for designing qubits at the circuit level. We have lots of tools for controlling qubits at the circuit level. We have very few tools for designing the fabrication process, computational tools. And that's what my group's been trying to develop for the last few years. Here is an example where we're actually oxidizing aluminium, and then we can put we're oxidizing, and then we can put the metal layer on top, and we do it atom by atom. Then we take that atomic model, and we have an electrical model. It uses a non-equilibrium Green's function approach for the people who know about those things. And we actually extract the IV curve from this atomic model. So we can put in defects. We can change the oxide concentration, we can change the stoichiometry, the density, and look at what happens in the electrical response. So for instance, here we see how the density, the stoichiometry, the coordination number changes during the oxidation process and during the metallization process. And then we can see how the charge flows through that resulting junction, all in the computer. So this is in silico design. We're really using a computer model to simulate the whole fabrication process. Now, the grand vision, of course, is to be able to predict things before we do these large-scale foundry tests. We're a long way from that, I'll be honest, but this is promising prototypes, I would say. The reason I've put it on this list is a really cool experiment that I had nothing to do with, but I'm very excited. It came out this year. This is an experiment led out of KIT with a bunch of other people, including some in this room, I suspect, where they looked at the corrections to the anharmonicity of a transmon, and they linked this to variations in the critical current with position in the junction. So the critical current varies across the junction, and that leads to corrections to this classic Josephson relation. The reason I'm excited is this is exactly what our computational tool was designed for. And sure enough, we can take a bunch of different junctions of different amounts of coverage, so we can stop the oxidation process early. So we've intentionally put pinholes in the process, or pinholes in the junction, and we can look at how the current flows through those regions. And then we can actually compute the current distribution in the plane of the junction from these atomic models. And the first thing you notice is, on the left there, see there's a big peak at the bottom? These are slices taken through the junction every couple of fractions of an angstrom. And you see that the peaks don't match up. So this is not a pinhole, just current going straight through. It wanders through the junction, even at this superatomic level. Yeah, very, very small distances, and you still see the current flow through. So we really need to work on uniformity of the junction in thickness, in density, and in stoichiometry, because all of these things lead to this kind of variance in the critical current, and the variance in the critical current leads to non-harmonic current phase response. So this is a theoretical calculation from this atomic model, which sees the same behavior that KIT see in their experiments. So this is me thinking that we need to improve our atomic models, but for once we were almost there in time, and my student's currently writing this paper up. So I'll finish with reminding everyone that this is the goal, yeah? We need to make some of the most perfect electrical circuits that humanity has ever built. Yeah? I know that MOSFETs are amazing and all of this stuff, but we're talking about quantum coherence here. Yeah? MOSFETs are just 0 and 1. Big deal. We need quantum coherence over a very long time period. So we need everything to be perfect. And my opinion is that having accurate theory models are a big part of that story. I've told you those 3 stories. I'm happy to discuss later. I would like, first of all, to very much thank my group, who's on the left there, who work on a bunch of different problems, but particularly Karen, Martin, and Jackson, who did a lot of the work that I talked about today, and of course my experimental colleagues in Sweden who do all the cool experiments. Thank you very much.
Okay, thank you for that very nice talk. I think we have time for maybe one question.
Thank you. I was wondering about these correlated shifts or like kicks on all the surface acoustic wave resonators. Could this be related to these issues with like micro cracks of the sample due to you know, the wax, or I mean, how it's glued to the PCB, or is it something that you would?
So to be clear, those aren't different resonators; they are different modes in the same resonator.
Yeah, but substrate would.
So why would they change? I mean, I don't know. We honestly don't know what the source is. But why would microcracks change on measurable timescales, like seconds?
Oh, because they can happen. Well, I mean, yeah, they can just happen, and it's like avalanche.
I mean, it could easily be.
This has been discussed in some papers. Maybe we can discuss later. Yeah.
Yeah. Okay, that would be good.
Okay, let's thank Jared. Our next speaker is Amir Osman, who will discuss mitigating frequency collisions.
Are you sure I'm next?
Oh, sorry. Okay, sorry. The next person is actually, is actually Harsh from TUM, and he'll be talking about enhancing the stability of superconducting resonators.
Am I audible? Okay, sorry. Cool. Oh, good. Good afternoon, everyone. My name is Harsh, and today I will be presenting our work in which we are trying to enhance the temporal stability of superconducting quantum circuits. The outline for my work today will be a introduction to the losses. I would like to thank Jared. He has already explained a lot of them to you and why they're important to us. And then we will follow it up with a way to get rid of those losses. And in the way which we are trying to achieve is through the self-assembled monolayers. Then I will discuss briefly about the passivation using these layers, and then their effect on the performance of the superconducting quantum circuit, especially the resonator in our case. So, as all of you know, the main adversary we have to face and want to defeat in these circuits are the losses. And the losses broadly can be divided into two parts. One is the internal losses and the external losses. Further, the internal losses, you can actually broadly divide them into power-independent losses and the TLS losses. The mainly power-independent losses are usually quasi-particle losses, which are temperature-dependent. And then you might have some eddy current losses. But if you look on this graph, particularly over here on the right, so this is basically nothing but the overall losses in quantum circuits at various powers. And if you see, the most significant contribution is actually coming from the two-level system losses. And also, as signified by this particular expression over here, these losses are really, really dominant when you operate at a very low temperature and very low power. And unfortunately, that's the regime we have to work when we work with these quantum circuits. But now the question is from where these two-level systems are arising in our system. So, already shown by Jared, but just to refresh again. So if you look into the system, actually, if you look in this particular cross-section of your circuit, you might after the fabrication, you might have some contaminants, some structural damages, and also you have some native oxide formed on your circuit. And these native oxide can host different ways from which two-level system losses can arise, namely the dangling bonds, hydrogen rotors, and atomic tunneling between two sites in lattice. So where all these so now the question is where are these losses are hosted in our circuit? So all the material, basically we use, all the surfaces and interfaces are expected to be the one contributing toward these two-level system losses. So namely, in our circuit, we primarily have a metal layer interface, which is a superconductor exposed to the air. Then you have a substrate air interface, where your substrate is exposed to air. And then you also have an interface between your substrate and the metal. So now the question is, if you want to get rid of TLS, and if you want to improve the performance of your system or your circuit, you have to get rid of this oxide layer. The thing is, you can get rid of this oxide layer just by etching. But the problem is that etching does not restrict the regrowth of this oxide on your material. So what happens that once you etch and take some measurement, and then with the time, the performance of your circuit degrades quite significantly. And our goal is to basically replace this oxide, or basically this surface layer, this metal layer interface with a layer with something which can passivate the surface and restrict the growth of native oxide again on the system. So to achieve this, what we are actually trying to do is a very novel method. So what we are trying to use is called self-assembled monolayers. So what are the self-assembled monolayers? Just to give you a brief introduction into this, they're actually nothing but a well-ordered array of organic molecules. These molecules can grow quite easily and quite effortlessly on the sample. Of course, you have to optimize a bit for that. Their thickness is usually around 1 to 3 nanometers. The specific self-assembled monolayers, or the SAM we will be using, are actually around 1.2 nanometer. And then you have a variety of choice of molecules to choose from. So a typical organic molecule with which you grow a self-assembled monolayer is basically having a functional head which binds to your surface, and then you have a hydrophobic organic chain. So different choice from the molecules you might have, like thiols, phosphonic acids, and the carboxylic acid. For our particular interest, we have used phosphonic acid. The reason behind choosing phosphonic acid is that they are easy to grow. They do not tend to form multi-layer. They usually grow very nicely in the monolayer form. And also, they can grow on a number of materials. So next, what we try to do is to passivate our niobium surface in the resonator. So what we do first is we etch out the oxide, topmost native oxide, and then we grow the self-assembled monolayer on top of the niobium resonators. So this, if you look, this is a schematic, not to the scale, of course, but this is somehow your self-assembled monolayer will look like. A very well-ordered array of the organic molecules, and where thickness is somewhere around 1 to 1.5 nanometer, which we have already calculated using lipsometry and also the AFM measurements. Next. So now, if you just look back, okay, now, as I have already mentioned, that we have a hydrophobic end. Now we say that we have grown the SAM, but we need to characterize it. And the most basic tool to characterize the self-assembled monolayer formation on any surface is to use a contact angle measurement. So I'll just briefly introduce what is exactly is the contact angle measurement. So what you do, this particular portion is your surface, mainly niobium, and this is nothing but a water droplet you put on your surface. All right, and this is the curvature, and then you take a tangent and the angle. This angle is basically your contact angle. And what it tells you that higher the contact angle, higher is the hydrophobicity of your surface. So if you have a really well-organized self-assembled monolayer on your surface, you expect a really high contact angle. And that's what exactly we are getting. If you look at these blue dots, these are the contact angle measurement for a passivated niobium surface over a period of 14 days. And you can clearly see the hydrophobicity is more or less stable throughout the 14 days period. Whereas if you look at the niobium, which has been etched freshly in the buffered oxide etched solution, the hydrophobicity is quite low and the surface is more or less hydrophilic in nature. So this actually indicates that we have a really good quality self-assembled monolayer on our niobium here. But to further look into the morphology, the effect of SAM formation on the morphology of these films, you could clearly see in the AFM measurements, the roughness is hardly changing. So we have a really uniform self-assembled monolayer formation on the niobium. But that's not only the thing. To further look into the footprint of the molecule, one of the spectroscopy you can use is the infrared spectroscopy. And this infrared spectroscopy gives you two different modes for CH2 and the CH3, the asymmetric vibration and the symmetric vibration. And the numbers which you see over here are actually quite close to the really well-ordered self-assembled monolayer for phosphonic acids which you can expect to form. Oh, sorry. All right. So now what we have achieved is the growth of niobium, self-assembled monolayer on the top of niobium. So then what we do is basically we take two different set of sample. One is a niobium resonator, which has been etched in the BOE in the similar fashion where we are growing the SAM, and the second one, which is passivated with this SAM. And now what we are trying to look at actually is that how well they perform if you try to age your resonators over the period of time. As we know, as you can clearly see in this particular graph, as you expose your niobium to the air, it starts forming oxide, which keeps on getting thicker and thicker in the nature. So that means if you have a resonator which has been etched, you take some measurement, but if measure it again and again, you expect degradation in its overall performance. And that's, OK, all right. But so to obtain these information, this is basically what scheme we have used. I think most of us are already familiar with this methodology. But what I want to emphasize is basically this portion. So what we achieve, we get actually the total internal losses in the circuit. And then we further look into the different kind of losses in our system. So, so we basically drive the low power losses, which are basically overall losses in your circuit, which are basically power independent losses along with the TLS losses. At high power, you expect your losses to be power independent, and then their differential basically gives you nothing but the TLS losses throughout overall TLS losses in your system you have. All right. So for the resonator which we are using in our study, basically the resonance is lying between somewhere around 4 to 7 gigahertz. All right. So now let's look at what happens when you age your niobium. So this data over here is actually shows the overall internal quality factor for a niobium resonator, which has been passivated and has been exposed to air for a number of period of days. You can see. So we have a fresh measurement of the Q factors, then after 2 days of aging, and then after 6 days of aging. And what interestingly you see, as expected, that there is a significant increase in losses when you age your resonator, which has not been passivated over a period of time. On the other hand, when you have a resonator which has been passivated with the self-assembled monolayer, you see a remarkable stability of the Q factor over a period of 6 days. You see there's hardly any change in the overall losses in our system. Further, to look more qualitatively into the overall losses, you can see here that relative change. And you will be really surprised to see that for unpassivated niobium resonator, the relative increase in losses is somewhere around 70 to 80%, and which is a really, really significant number. Whereas in case of the passivated resonator, you see almost no change in the losses. So the performance is really, really stable and really precise over a period of 6 days. Now, further to try to little bit dig into detail at what losses are exactly responsible for this degrade in the performance. So if you look into the correlation between power-independent losses and the TLS losses, which we have extracted from the Q factor information we have, you could clearly see that for the passivated niobium, you clearly see an increasing trend, a linear trend, when you, sorry for this is basically power-independent losses. I don't know why it is not showing clearly here. And this is the TLS losses. So you see a trend a linear trend in the TLS losses when you plot it with the power-independent losses. And this clearly signifies that most of the losses which are occurring in our system when we are exposing it for a period of time are actually due to the different two-level system losses. Whereas in case of passivated resonator, you can clearly see there is no increase, there is no increase in the overall TLS losses when we look into the correlation between power-independent and the TLS losses. But now the question comes is, why do we see this trend? All right. So what do we expect actually by the passivation of niobium layer is actually that we are hindering any more growth of the oxide on the niobium. So further to look into this, we have done some X-ray photoelectron spectroscopy. And here you see basically the phosphorescence spectra. This is basically just to quantify the presence of phosphonic acid molecule on our surface. Here you see a phosphorus group with different contribution coming out from the different bonding scheme of the phosphorus. But more interestingly to us, if you look into the niobium spectra of X-ray spectroscopy, so for this we have actually aged our niobium in a similar fashion in which we have aged our resonators over a period of time. So when you age your niobium over a period of 6 days or 1 week, you clearly see in these two graphs, actually, these two peaks are which are coming out from the elemental niobium you have in your system. And when you do not passivate your niobium, you clearly see a damping of the elemental niobium signal. And this damping of elemental niobium is basically due to the thicker oxide formation on top of unpassivated niobium, which you clearly don't see when you passivate your niobium with this self-assembled monolayers. So to quantify it further, actually, if you look into this bar graph, this actually shows the overall contribution from the elemental niobium to the overall niobium peak spectra in the XPS. And you can clearly see the passivated niobium actually shows a significantly higher elemental niobium contribution in comparison to the unpassivated niobium. And that is basically due to the thicker oxide formation on the niobium. Not only this, even if you look into the valence band spectra for the same system, you see a really, really interesting data over here. You clearly see a significant metallic niobium 4D character in the passivated niobium in comparison to the unpassivated niobium. And also overall reduced contribution coming from the hybridized state of niobium and oxygen on the circuit. So this basically really established that with the SAM formation, you really restrict or hinder the further oxide formation on the niobium. So now just to conclude, so what we have achieved here is a growth of highly ordered self-assembled monolayer on the niobium, which has been etched or stripped out of its oxide. Then we really achieve an improved temporal stability of the resonator performance. So basically, we have almost consistent Q factor values over a period of 1 week. Also, this is actually attributed to the restricted growth of oxide formation on the niobium. But further, there are plenty of things actually has to be explored. So we also have to see actually how the loss tangent of these self-assembled monolayers are there. We do not have any sufficient information yet, but we would like to look into that. Also, further, we would like to apply this process on a whole qubit chip and to see how it affects the overall performance of a qubit chip. And also, we can now further looking into explore different molecules and different length of the organic molecules that can be used to grow self-assembled monolayers. At the end, I would like to thank all my colleagues at here, Tum and ZyteLab, other colleagues at ZyteLab who has helped to fabricate and grow different self-assembled monolayers out of the process. I'm highly thankful to MQB. And that's it. Thank you.
OK, thank you for that very interesting talk. Are there any questions for Harsh?
Yes, thanks for the nice talk. If I remember your graphs correctly, the passivated resonators had lower Q factors than even the aged niobium.
Yes.
So do you know where this comes from? Is this like dielectric loss in your monolayer, or?
Yes. So we are actually investigating this. One of the things is that when we are growing SAM right now, we have to grow. The process is actually 48 hours long. So one of the idea we have that it might be due to that time in which we are growing SAM, we are incurring some other losses which we are not aware of. But right now, we are actually working on to improve the process to reduce the time of deposition of the SAMs, so we would have a better idea whether it is coming out of SAM or some other losses which we are incurring during the process.
Thanks.
How robust is the passivation layer? Like, if you have following fabrication steps, does it go away easily, or can you put it back?
All right. So they can be grown really easily. The process is actually compatible with CMOS technology, at least. They can withstand a temperature up to 120 degrees Celsius to 140 degrees Celsius. But yes, we have not actually analyzed that specifically on this material. But throughout the literature, it has been established that SAM are really, really stable for 100 degrees Celsius to 140 degrees Celsius temperature. They can easily withstand that.
OK, let's thank Harsh again.
Thank you.
OK, now I think for real this time, Amir is going to discuss mitigating frequency collisions.
Thank you. It's a pleasure to be here. My name is Amr Osman. I'm a PhD candidate at Chalmers University of Technology in Sweden. And my work has been part of Open SuperQ, the European flagship, and the Wallenberg Center for Quantum Technology. And the goal of the center is to build a 100-qubit quantum processor. And of course, several challenges appear when you try to scale to such a big number of qubits, and one of these challenges is frequency collision. And today I'm going to talk to you about our efforts in mitigating this problem on a quantum processor. So a quantum processor typically consists of a lattice of interconnected qubits, And this lattice can be a square lattice. In our case, we use the parametric gate architecture, where we drive 2 qubit gates between fixed frequency coupled qubits via a tunable coupler. And basically, any sort of quantum algorithm you implement on this processor is a combination of single qubit gates, where you drive microwave pulses at the transition frequency of these qubits, or the qubit frequency, and 2 qubit gates, where you drive the tunable coupler with a microwave pulse at the transition frequency between the different states of the 2 qubit manifold. For example, if you want a CZ gate, you drive this coupler with the transition frequency between the 1-1 and a 2-0 state, or the 0-2 state. If you want to drive an I swap, you drive the coupler with the transition frequency between the 1-0 and the 0-1 state. And it's very important here to choose these transition frequencies such that neighboring gates are not too close to each other in frequency. And the reason for that is that there's always crosstalk between lines carrying control signal on a quantum processor. So, for example, if you are driving this coupler here with a certain gate at a certain frequency on a control line, part of this signal travels to the neighboring control line. And if the two gates are too close to each other in frequency, you will end up driving the wrong gate on the wrong coupler. So what we try to do here is that we separate neighboring frequencies from each other as much as possible. But in reality, when we go to the clean room to fabricate these qubits, they deviate in frequency from the design parameter. And you end up having neighboring gates colliding with each other in frequency. And in presence of crosstalk, the fidelity goes down. So how do we fix this? To start, we use the transient qubit frequency. And you can express the transient qubit frequency as a function of both the EJ, the Josephson energy, which can be expressed in terms of the junction's normal state resistance as such. And everything else here is a constant. Delta is a superconducting gap of aluminum. Phi naught, of course, is the magnetic flux of quanta, and E is the electron charge. The frequency also depends on the charging energy, EC, which is dominated by this large shunting capacitor with the junction. And it's shown here on this micrograph as a cross shape. It's a planar capacitor that is 5 or 6 orders of magnitude bigger in size than the junction. So basically, if you want to have reproducible qubit frequency, you need reproducible resistance and reproducible capacitance. So far, the bottleneck had been the reproducibility of the junction resistance. So that's what we spent some time during the last few years improving. So I'm not going to go into so much details on how we fabricate the junctions, but we make Manhattan-style junctions where we pattern such a cross on a resist stack with electron beam lithography. We evaporate one electrode at a 45-degree tilt and then oxidize to form the oxide barrier. Then we rotate the wafer 90 degrees and deposit the second electrode. And the junction is formed in the overlap in between the two electrodes. And this is how the junction looks like under SEM. So it's basically the overlap between these two electrodes. And any variations that come from the junction is coming from variations in the area of this overlap and the thickness of the oxide layer in between the two electrodes. And that's what we try to fix. So how do we characterize the reproducibility of our junctions? So typically we fabricate about 3,600 junctions on an area equivalent of 2-inch wafer. And we characterize the resistance with an automated probe station using 4-point probe measurement, which can measure these thousands of junctions in a matter of 3-4 hours. This is an example heat map of how the resistance varies over the wafer with windows of 5 by 5 millimeters squared. And if you plot the junction resistance as a function of the junction size on a log scale, you would get this line, given the relation between the resistance and the area. R is proportional to 1 over the area. And more importantly, if you plot a histogram for the distribution of the normalized resistance of every junction size, you'll get an almost perfect Gaussian distribution with a sigma that narrows down with bigger junction sizes. And then if you plot this sigma as a function of the junction size, you see that it's highest for the smallest junctions, and it goes down with larger junction sizes. And the average standard deviation for the junctions we chose here is about 3.7%. And for junction sizes of interest, which we use to make qubit frequencies between 4 and 6 gigahertz, the standard deviation in resistance was between 3.5 and 5.5 and 6 gigahertz, which translate about 1.7 to 2.7 in fair wafer level standard deviation in qubit frequency. So we wanted to improve on this further, and the improvement is motivated by this curve here. So basically, instead of making small junctions where the standard deviation is high, why don't we make slightly bigger junctions where the standard deviation is lower? The only problem you face here is that if you make bigger junction sizes, the resistance is going to be lower, and the target, the frequency is going to be over range. And the most straightforward solution in this case is to increase the thickness of the oxide layer. And this is because the resistance is proportional or exponentially dependent on the thickness of the oxide, and it's proportional to 1 over A. So if you want to increase A, you need to increase the thickness of the oxide accordingly in order to achieve the same target frequency. And the way you increase the thickness of the oxide is simply by increasing either the oxidation pressure or oxidation time, or both. So we tested that. We wanted to see how much the unit area resistance increases with the oxidation dose. And as we would expect, the higher the dose, the higher the unit area resistance. And here we define the dose as the oxidation time multiplied by the oxidation pressure. As you see here in blue, circled in blue, these are the old oxidation parameters that we used before, for which I've shown the data so far. And in red, these are the new oxidation parameters that we decided to move to with the smaller deviations. And the reason we chose these specific oxidation doses is that this is the dose that will allow us to make junctions with these low variations and these sizes while targeting the exact frequency that we want. So we repeated the reproducibility study again. It was important here to make sure that the higher dose or the thicker oxide does not deteriorate the quality of our junctions, so it doesn't shift the standard deviation. But in fact, we found that the standard deviation curve is even lower, which might indicate that the thicker oxide leads to a more uniform resistance. But more importantly here is the gain we have by making larger junction sizes. So here we fabricate junctions with standard deviation of about 2% instead of about 4%. So what does this mean for variations on the wafer in terms of frequency? We can simply use the Transmin frequency equation again, and knowing that the standard deviation in frequency is half the standard deviation in resistance, we can map the data from this curve to this curve here. And we see that for qubit frequencies between 4 and 6 gigahertz, the standard deviation is around 45 megahertz. But this is what we infer. We wanted to make sure this is what we actually get if we make qubits and we cool them down at low temperature. So we tested that. I fabricated 32 Transmin qubits with fixed frequency, junction sizes of 0.33 by 0.33 micrometers squared, cooled them down to 10 milli-K and measured the frequency. And indeed, you see here a distribution of the frequency of these qubits. The standard deviation, the mean is around 4.6 gigahertz, and the standard deviation is around 40 megahertz. In fact, at such a low level of standard deviation in frequency, there is even a non-negligible contribution from the charging energy that we should start taking into account. And that was around 0.8%. So we can see basically at this point that there's almost an equal contribution from the resistance of the junction and the capacitance of the big charging capacitor. But we believe it's probably easier to improve the EC further, either by using e-beam lithography to make the qubit capacitors, if lithography is the problem, or using dry etching instead of wet etching, which we use currently in our case. So what does this improvement mean for our quantum processor? Of course, if you reduce the spread, you reduce the anticipated collisions on a quantum processor. But quantifying this really depends on what kind of architecture you're using, what kind of gates you're implementing. So we decided to test this for the architecture we're using for the parametric gates. So we ran a simulation where we assign each qubit here a target frequency that will not lead to any sort of collisions between gates. However, in this assignment, we add a standard deviation that mimics the error in the fabrication process. And then we see how many times two neighboring gates got too close to each other than a certain threshold. And if they got closer than a certain threshold, it's counted as a collision. And this collision depends on the target gate fidelity that you want and the amount of crosstalk you have on the chip. So as an example, if the target gate fidelity is 99.9% and we have 2% crosstalk, we expect the number of collisions to be around 2.5 for the 40 megahertz case on a 100 qubit quantum processor, which drops down from about 7 collisions with the old 120 megahertz standard deviation with the small junctions. Ideally, we would like to be somewhere between 10 and megahertz here, but we're not there yet. However, here what matters most is not really the absolute numbers. It's about the comparison between the different cases, because this number will depend on different factors, like the amount of crosstalk you have. So for example, if you have 10% crosstalk instead of 2, which is a bit of an extreme case, you will have 5 times more collisions in all the cases. And of course, there are things that we haven't considered in this simulation, for example, the decoherence of the qubit and how it contributes to the fidelity, and how optimized is the pulse. Finally, we wanted to see if there's any downside of making these large junctions, or a price we pay for the low spread in frequency. And basically, it's known that the oxide barrier of the junction hosts 2-level systems, defects, like any other interface on the substrate. And these TLSs, they have a certain density. So basically, if you increase the area of the junction, you would expect to have a higher probability of hosting a TLS inside this junction. So we wanted to probe this. So we did a TLS spectroscopy experiment. Here, we tested 4 tunable squids, 2 large junctions qubits, and 2 small junction qubits. So what you get from a TLS spectroscopy experiment, basically a trace for the lifetime of the qubit as a function of its frequency. So these are 4 traces for the 4 qubits we've tested here, 2 small and 2 large. And every peak you see in every trace here corresponds to a TLS at that frequency. But in fact, none of these TLSs is inside the junction. They're all TLSs outside the junction, except this TLS here in qubit number 2. And we know that it's inside the junction due to the coupling strength it has. So it has about a coupling strength of 7 megahertz. In fact, this TLS was even persistent in between 2 cooldowns. It just shifted in frequency about 200 megahertz. And finding 1 TLS in the 2 large junction qubits was something to be expected with a probability of about 50%, given the area, the total junction area of the 2 qubits, which is 0.35 micrometer squared. And assuming that the TLS density is 1.5 TLS per gigahertz per micrometer squared, and we got this data from this reference here from Lisenfeld in KIT. And if we use this 1.5 TLS per gigahertz per micrometer squared, and we try to do a simulation to see what is the probability of having one, or how many qubits on average on the 100-qubit quantum processor are going to be colliding with a junction TLS. So the results gave us only 1 qubit on average, but with the smaller junctions, this number was only 0.3. So there is slightly higher probability of having one qubit colliding with a TLS on a quantum processing unit. So that's all what I wanted to present for today. We achieved 40 megahertz spread in qubit frequency with 3 times less anticipated collisions based on the architecture we're using. We expect to be also gain and lower number of collisions for different architectures, but to quantify this, you need different studies. Qubits maintained high quality factors, and TLS spectroscopy showed that we expect about 1 TLS on a 100-qubit quantum processor. And we think that this is sufficient for us to scale to 100 qubits. Thank you for listening, and I would like to thank everyone involved in this work.
Thank you for that nice talk. Are there any questions? Yes.
Yeah, thanks a lot, Amr. Fantastic talk. What is the JC that you actually used, microamps per micron squared? We had tried a similar thing a couple years ago. We also found an increase in TLS density. And so we decided to bump up the JC a little bit more. But I'm just curious. I mean, I could calculate it, I guess. But do you remember what the critical current density is?
Yes, that was about 900 nanoamps per micrometer squared.
Okay. So, yeah. And so in your scheme of 100 qubits, do you need to do any fast flux biasing, or are you just doing parametric type gates?
We're doing parametric gates.
Parametric gates, okay. Thank you very much.
Yeah.
Thanks for that talk. Can you go back to slide 98? I had a question about a plot.
Which slide?
98, I think it was. Yeah, that one.
Yes.
So I'm just looking at on my left the red and green, red and blue plot, and red and blue plot. And it looks like there's some correlation between the data. I might be imagining it, but if I just look at the blue squares and the red squares, they both seem to be up and down relative to the fit in some sort of correlated way. And I'm just trying to understand why that might be, apart from just imagining it.
You mean the correlation between the two curves or the fits?
The data. If I look at the data there, it looks like where there's the blue dot's high, the red one's typically high, where the blue one's low, the red one's typically low.
Yeah.
And I'm just wondering why that would be.
Yeah, actually when we did this, we were just hoping that at least they are overlapping. But what we saw here is that the red curve with the thick oxide, it shifted down. Usually if you have a downshift in the standard deviation curve, it's attributed to the uniformity of the oxide thickness over the wafer. And the change in the curve with different junction sizes, that's attributed to the variation in the area. Because smaller junctions are more sensitive to variation to the area, the curve is higher in the beginning. And the shift is just the offset is caused by the uniformity of the...
So I'm not talking about the shift, I'm just saying, if I look at any particular junction area, the blue dots, when they're high, so are the red dots, and when the blue dots are low, so are the red dots. And it looks like they're correlated, and I just don't understand why that might be.
Yeah.
Maybe I'm imagining it, but we could.
No, actually, that is correct. That is correct. The issue here is that these sizes they map to certain sets of probes on a probe station, where the probes are faulty most of the time. So you have basically less sampling of these sizes. So it contributes to a slight shift in the standard deviation.
Okay, let's thank Amir and all the speakers in this session. And then Stefan has a couple of announcements regarding the tours that people may be going on.
Thank you. Thank you. So I have just some organizational announcements regarding the tours we have next. If you're signed up for the QTRA tour, we would kindly ask you in like 10 minutes to meet at the reception desk because we go there by bus. You'll see the QTRA guys there. They will accompany you there. For the Munich City Tour, everyone essentially can join. That will leave at like 6:10, 6:15. WMI and LRZ are leaving at 6:30, and until then, we have the Blue Force Happy Hour going on downstairs, which means there is food and drinks around, so we can enjoy ourselves, network a little bit, discuss what we learned today, and I wish everyone a great evening. If you're heading for city center, for example, for the city tour or something else, we have public transport tickets downstairs for you, so we will distribute them. One very important thing to remember from Munich is you need to stamp them. There are machines where you put them in to stamp them, otherwise you're like illegally on the subway. That's important to keep in mind. So enjoy your evening, have great discussions, and see you later tomorrow morning.